All right, so I think we should go ahead and just get it started. So welcome to Santa Barbara, welcome to SoCal NLP 2022. And we're so glad that everybody's here. My name is William Wang. I am one of the faculty advisors at the event. So it is my great pleasure to tell you a little bit about the background of the events and give you a little bit more about the statistics about our SoCal NLP faculty. So just a little bit about the COVID-19 guidelines. So we follow UCSB COVID guideline for visitors, and if you need any help, if you need a mask, we have a mask at the registration desk. But just let us know if you need any assistance, right, about any requirements that you may have. So that is, something would be good to know. So the main point of me standing here is to show you this figure, right, of amazing growth of NLP research and faculty and new labs at the, SoCal area. So started, I think, this particular wave, right, of growth, I think started in 2016. Samir and I and John are sort of like one of the earlier people who got here in SoCal. And then Kai Wei, DAPA, and Xiang got here in 2017, 2018. Taylor moved from CMU, and Jingbo and Peng Tao, Nanyun, they all got to their current positions. And then also we have teaching faculty. Zenda is at Harvey Mudd. So this is sort of like 2016 to 2019. 2020 to 2023, I think is the growth is even more significant, that we have new research assistant professors at ISI, Xue and Mu Hao, and Zhiting joined San Diego, Lei and Shiyu, our co-organizers this year, joined UCSB, and of course, everybody knows USC has been doing amazing in recruiting. They have Jesse, Robin, they're both here, Swaba will give a talk very soon, Dani and Jieyu in recent years, and also very happy to report that finally, UC Riverside, we're going to see a new NLP faculty starting next year. So this is really wonderful news, I think, for the entire NLP faculty in the SoCal area. So I did a little bit of plot, right, trying to analyze the growth, right? So I think this is really healthy, right? So we started with, 3 new faculty in 2016, but then now we have 20 to 22 new faculty in the SoCal area. But of course, I cannot resist the urge of asking our friend GPT-3 to give us some predictions, right? And of course, the proper way to give in-context learning is to give some context, right? So I said, SoCal NLP academic labs are growing rapidly. Here are the numbers. What are the projections, right, for the next 5 years? And so I tried, tax DaVinci 2, 002, and it told me that we should get to 37, right, in 2018. So this is, very useful advice for the faculty recruitment committee. And then, of course, given that I already tried this, why don't I try like, Codex, right? But Codex, for some reason, I only asked one question. It then asked another 4 or 5 questions for me. So it actually gave, additional questions automatically, and it started to ask about 2052. And the final projection is that we're going to get, 109 NLP faculty in 2052. I don't know. It's a little hard to tell, right? I mean, that's going to be really far away. But this is just, some projection, okay? But a little bit about the history, right? On the more serious side, the history of the event is that, we started this event in UC Irvine. So Samir and I, we were the faculty co-founders of this event. And then we started, with 30 posters, 5 speakers, 4 contributed talks. And in 2019, Nanyun and Zhongmei, they had another wonderful event in USC in 2019. So that was really before the pandemic. And then the pandemic hits. In the last 2 years, we had a hard time getting people together. Taylor, DAPA, and Jingbo, they did a wonderful job organizing this a virtual event online. But I was talking to Jingbo this morning, we should really do it again in person in San Diego too. So, but that was a combination between SoCal Machine Learning and SoCal NLP event. This year at UCSB, we're happy to report that we have 88 posters, which is a huge growth in terms of student participation. And I'm happy to tell you that yesterday we have received more than 213 registrations. You're going to see more people coming in and out in the afternoon and today. So this is, I think, really a wonderful opportunity, right, for people to get to know each other. And I really want to thank people who make this event possible. I want to thank our wonderful student program chairs, Michael and Yujie, for their hard work getting, the reviewers and, getting the paper reviews and getting, best paper award selection and all that. So Michael will tell you more in just a second. Of course, this event is not possible without, our faculty advisor Lei Li and Shi Yuchang. They did amazing work to really make this event happen. And without our, organizing committee, Zhen Qiao, Dan Qing, Qiu Chen, Ke Xun, and Laura, this was also impossible to really, get it to work with all the logistics. And what I'm going to do next is, of course, I'm going to thank our sponsors, especially at this very difficult time in tax recession. We're so lucky to have our support from Megagon Labs, who has a booth over there, and our friends at Folio also has a booth over there. Amazon, also, we really appreciate their help, right? That was, sort of, very good, timing. We were able to get it to work. But it is, certainly a difficult time for, I think, for the industry, but we're so glad that we are able to get their help in organizing this event. And of course, UCSB's NLP group and the Center for Responsible Machine Learning also contributed to make this event happen. Now I will introduce our program chair, Michael Saxon. He will tell us about the statistics and structure of today's event. Let's welcome Michael.
All right, hi everyone. So I am the co-chair, but Yujie couldn't make it, so I guess I am the acting sole PC chair. So, no, I'm kidding. Welcome everyone. So a little bit about the statistics for the submissions. Great job, USC. You guys really sent in a lot. But collectively, University of California, sorry, public wins. We've got a lot represented. We have Santa Cruz here, we have Irvine, San Diego, Los Angeles, Santa Barbara, of course. And next year, we'll get Riverside, and we'll have full coverage of the SoCal area, so that's very exciting. And then also, we have some first author institutions from outside the region, too. We have 3 papers from CMU in our poster session. We also have submissions from Boston, University of Michigan, Columbia, and even from University of London. I don't know if they were able to make it, though. I don't know if we made it clear that this was in person only in the call for papers, so. For the reviewing process, we put together a PC of 32 members, and they all did a lot of work because we did not anticipate getting 88 submissions. It's very exciting, of course, but as a result, I kind of had to send out some emails like, please forgive me. Please forgive me, I assigned you 8 papers, but just read them really fast, don't, no detailed comments, and we tried to get 2 to 4 reviewers for each paper. We were mostly able to achieve that. And then each reviewer rated the paper on we weren't doing a super strict like acceptance, technical rigor stuff, but we were saying, okay, is this something that we want to highlight as being worthy of an award? Because thanks to our sponsors, we actually have 3 named Best Paper Award winners, and the first author of each of those will be getting a $300 prize. And yeah, stay tuned to the closing ceremony where we will be announcing all of those best papers. So I want to thank all the program committee members, and especially I want to thank the program. Oh. Well, that's odd. It's still plugged in. Should I just plug it in? Yeah, can you help? Oh, okay, it's back. Sorry about that. So yeah, I want to especially thank all of the program committee members from outside of the region who volunteered to help with reviewing even though they wouldn't even have a chance to come here. So Suhong from University of Connecticut, Maitreya from ASU, Joel from UT Austin, Yunting from Stony Brook University, Tian Lin from University of Chinese Academy of Sciences, and Franciel from University of Sao Paulo. So I want to thank all of them. If any of you are watching the stream, thank you very much. And yeah, that's about it. So I'll call up the first session chair, our Professor Lei Li.
Wonderful. Welcome, everyone. So I'm Lei from UC Santa Barbara. I will be hosting this first morning's session. We have two wonderful speakers to talk about how can we deal with these gigantic, large models we can't even fit on a single machine. So our first speaker will be Professor Yejing Cui from University of Washington. Please. So maybe you can set up. Yejing Cui is Brett Hessel Professor at the Paul Allen School of Computer Science and Engineering at University of Washington and Senior Research Director at AI2. So she, of course, is famous for her numerous work on common sense reasoning, natural language generation, grounding with vision, and also AI for social good. So we will hear some of the talk, but for each of the area, she actually won multiple Best Paper awards, including 2 Best Paper awards this year in NACO and ICML, and 2 Test of Time Award last year, ACL, if you still remember, ACL last year, and CVPR, Test of Time Award. And NeurIPS Best Paper Award last year, and AAAI Best Paper Award, and ICCV Best Paper Award. I couldn't stop. I should ask GPT-3 to predict what's the next venue she's going to publish and get the Best Paper. And of course, very recently, that's really after we invited her, she got the MacArthur Genius Award. That's a top award for an encouragement for the whole NLP community. So without further ado, we'd like to hear more on this, how to dealing with glass gigantic large neural models.
Well, thank you so much. I feel very overrated now. David and Goliath, the art of leaderboarding in the era of extreme scale neural models. See whether okay. We hear that GPT-3 is amazing in these early sessions as well. And so journalists ask me whether I'm really sure that we cannot reach AGI just by scaling things up. And I don't know how to defend. And then some students and professors even worry in academia whether we can do impactful research without such compute. So let's draw inspirations from old wisdom, especially the art of war. The wisdom is that know your enemy, choose your battles, and innovate your weapons. So, of course, in the new modern deep learning era, you need to reinterpret that as evaluation with the scrutiny and realism, including adversarial, out-of-domain distribution evaluation, and choose your battles through different tasks, harder tasks or realistic tasks, and then innovate your weapons through algorithms and data. And in this talk, I'm going to tell you about 2 different threads of such research, symbolic knowledge distillation and decoding algorithms. And the underlying theme, recurring theme, will be the smaller but better, and knowledge is power. So let's begin with the first one, causal common sense models. That's distilled from neural language models. Why do we care about common sense? Well, despite human level or even superhuman level performances, neural models do make silly mistakes that humans would never make. So it's almost as if deep learning today knows how to solve a data set without really solving the underlying task reliably. And so why does this happen is that, well, humans really learn the concept and the knowledge about how the world works, whereas machines learn some patterns from the raw data, which is hard to interpret, And so is there a way to bridge this gap? So one of that challenge, really important one, is common sense knowledge and reasoning. For the purpose of this talk, I'm going to define it as the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people. It's very important that this is just shared by most people, not every single one of us, because it's the kind of knowledge that can vary depending on your cultural backgrounds and situational backgrounds and so forth. So, for example, generally we think it's okay to keep the closet door open, but not as okay to keep your fridge door open because the food inside might go bad. But you can always add additional context to defease this inference. So for example, if the fridge is not even plugged into the wall, doesn't matter. So these are basically rules of thumbs that humans rely on to live and interact with each other in a reasonable and safe way. And AI, as it becomes more integral in our day-to-day lives, does need to learn about such human needs and actions better. So language models, by the way, they're not equivalent to knowledge models. We do need to think about knowledge models as the first-class citizen of research goals. So for that, we studied both the symbolic common sense knowledge graph as well as neural common sense models that's trained on top of a symbolic knowledge graph. And up until 2 years ago, everything for the symbolic side was fully crowdsourced. And I highlight that because in this talk, we're going to lift that. But anyhow, so there's a follow-up, Comet Atomic 2020. Let me give you a quick summary example of what it looks like. So imagine X gets X cars repaired, or you get your car repaired. And for that, you can imagine that, well, as a result, I might need to call taxi, Uber, Lyft. Before then, I need probably some money and need to find the mechanic. So these are event-centric knowledge that's in Atomic. It also now, the new one, 2020 version, includes object-centric knowledge. For example, money can be used for paying bills. But if you really want to do so, you can also fold that into origami. I've never done that. This says something about stereotypical use cases as well as physically possible affordances of objects. So it requires both naive physics knowledge as well as your everyday just functional knowledge. You can also reason about counterfactual situations in which this center event cannot happen. So your car is totaled, then you cannot get it repaired, and so forth and so forth. So we crowdsourced quite a bit. I mean, you know, like GPUs are wonderful and all, but so are humans. And instead of only paying for your compute, we can also pay people. So we collected 1.3 million if-then inference rules over 23 different edge types. So all these different edge types are different common sense inferences. Again, fully crowdsourced. What good does that provide? So this is a quick summary. Here you see our Comet, little guy, compared to GPT-3, which is so large, it doesn't even fit into the slide. It's more than 400 times, this guy is larger than this Comet. And so, but Comet is trained on the symbolic knowledge graph as if it's just text corpus, in which case, when we do this common sense inference as generation task, so given a center event and some relation type, you have to produce some reasonable common sense inference. This is what I would call as generative evaluation. And so we ask humans, what do they feel about the generated inference? And so in terms of a precision, Comet is much better than GPT-3, but this guy's remarkable considering how it's trained on raw text, and especially how GPT-2 used to be so bad. So 73% good. We'll get back to that, as well as the fact that GPT-2 is this bad. But for now, I'll just highlight that when we put out resources such as Comet and Atomic, people all around the world start doing creative things using them. So some examples include the storytelling and fantasy gaming, and also in an interactive learning environment based on cell phone. Tom Michel and other co-authors did some interesting work. So we wanted to improve this resource, but just crowdsourcing more and more was hitting a bit of a wall. It's not just deep learning hitting the wall, by the way, it's also the crowdsourcing that can hit the wall. So we decided that we're going to do something with this GPT-3 guy, but it's too large. I don't have the kind of a compute to fit it into my computers. So what we do is going to be symbolic knowledge distillation such that it's going to be smaller but better. How is that even possible, though? Because usually what happens when you make a large model smaller is that it gets worse. In this case, it's going to be possible in part because this funnel is a weird one, that's convoluted one, with the critic in the middle. It's also in part because compared to the original knowledge distillation due to Hinton, Jeff Hinton, and other co-authors, for which you teach a student model based on the teacher model based on this cross-entropy between the two. And here, the premise is that the student model is of the same type as the teacher model, whereas in our case, we want a different model. Basically, GPT-3 is not necessarily common sense model, but we want common sense model out of it. So there's one difference. The other difference is that we don't do simple classification, but rather our output space is a sequence. Of course, we cannot do this computation exactly, and you are going to just sample and then call it a day. It's just say that this is a good approximation of it. A nice byproduct of this sampling, though, is that you can interpret that sample into this knowledge graph by connecting repetitive concepts, and so you get this interpretable symbolic knowledge graph. So what happens with that atomic, machine-authored atomic, we're going to name it as atomic 10x. So compared to the original atomic 2020, entirely written by human, so here, for this study, we only look at 7 relation types. So it's a small subset of the entire atomic relation types. So what you see, y-axis is the quantity in millions. So there was less than 1 million atomic 2020, the human written ones, versus atomic 10x by GPT-3. This is very large. It's more than, almost like 7 million. But the problem is, this is not very good. So the black portion is the bad portion. So you remember this is about 73% good. So then what we do is we train a small model, critic, it could be based on anything, but in our case, Roberta, based on moderately sized, annotated examples of what's good knowledge and what's bad knowledge. Obviously, this is not very good either. This guy doesn't really have a common sense knowledge. So it's primarily deciding this based on surface patterns. But it's good enough to remove most of the black portion, together with a lot of good stuff. But nonetheless, the end result of this is that now we have, for the first time, a knowledge graph that's bigger than what human wrote, and yet of better quality. By the way, humans don't necessarily agree with every single common sense bit, like I mentioned earlier. So what does that entail in terms of the downstream model performance? Because we remember GPT-3 was about 73% good. Now, if you use that as a direct teacher to train a student model, it turns out on its own, the performance goes up. Why that's the case, I'm not sure. So perhaps we can discuss that further later. But it turns out still that's not as good as this Comet trained on human-authored atomic 2020. But finally, if we use the critical teacher that combines, it's almost like a product of expert between GPT-3 and the small Roberta critic, then the resulting knowledge graph will enable training the downstream model that performs the best so far. So that's exciting result. So to summarize, for the first time, we have this result such that machine-authored knowledge graph is just better than human-authored one over all criteria, scale, accuracy, and even diversity. So we measure diversity in many different ways. Here you should just see a unique 1 gram count, but we also report other measures. And so, yeah, GPT-3 is pretty good, so long as we use it through some algorithmic filters. But, you know, some of you may think, I don't care about common sense knowledge. I care about summarization. So let me be very brief with the next 3 components. So this is work coming up at EMNLP, reference-free sentence summarization. So never mind supervised data as much anymore. So GPT-3 summaries, according to a new paper from UT Austin, it's really the best summarizer, better than all the other supervised models. So that's depressing. But the good news is that if you actually look at GPT-3 summary, a lot of them are too long, and also they're not, you know, like, there's a room for improvement, I would say. So this shows the length of the summary. A lot of them are too long. They don't sometimes summarize very much. So keep that in mind. Let's just see whether we can do symbolic knowledge distillation on top. So of course, we want something better, especially, I don't know, like, feel like GPT-3 is amazing, but we wish something smaller that can summarize with varying degrees of compression rates and yet somehow better. So in this particular case, we designed the filter to have 3 layers. Fidelity filter based on natural language inference, off-the-shelf natural language inference model. Actually, what did we use? I think we may have used Wangni. That I'm going to talk about in a bit. And then length filter, so that we throw away summaries that are too long. And then there's information bottleneck filter based on information bottleneck principle. But this part is not that important. But the quick summary view is that we, in this case, do this iteration, distillation through multiple iterations, student teaching another student, teaching another student for about 7 times. And it turns out this is a good idea. It keeps getting better and better at learning to compress at desired ratio while keeping the quality as before. So that's a quick summary of what we can do with this symbolic knowledge distillation framework. And then, okay, maybe you don't care about summarization either, but care about natural language inference. So here, the work is a little bit different in the sense that we're going to focus on, oh, hi, Swapa here. The work is a little bit different in the sense that we're going to distill data set now. So MNLI seems to be the de facto, you know, the most standard data set to use when you want to train NLI models. And that leads to relatively poor performance when tested on all these like out of domain or adversarial test sets. So these are all different NLI test sets developed by other researchers. And ideally it should be at 100%, but compared to MNLI performance, all these results are much less. But we have this new Wangni data set that's 4 times smaller than MNLI data set, and yet the out-of-domain performance is better across the board. So, I mean, don't you love this kind of situation where the smaller is okay, and it can even be better? So how did we do that? So it turns out MNLI dataset was originally created by asking humans to write the entire thing, but and humans are, human intelligence really overpowers AI in many ways. However, when asked this particular way, they tend to repeat themselves. They also have like cognitive biases, and so there are a variety of research reports that says basically that there's annotators' biases that swap here too. Now I realize. Yeah. So in the meanwhile, GPT-3, people say it's good stuff. So can we do something with it? So what we do is we draw on this previous work called dataset cartography, also with SWAPA as the lead author, that gives you some insight about dataset such that it has regions. So here you see any given data set, you can map it as if you're a cartographer into regions that are easier to learn versus ambiguous to learn versus just impossible to learn, difficult to learn. So the third region usually is about label errors. Now this part is interesting, ambiguous region. There are not that like many items sometimes in this region, but that can be the powerful one, it turns out empirically, for out-of-domain generalization. So then what we do is let's just make more of them by giving the ambiguous examples as prompt for GPT-3 so that it can generate some similar NLI examples. But of course, GPT-3 doesn't really know inference correctly, so it's gonna require filtering. When we do this filtering, we use ideas similar to dataset cartography again, but then even then it needs human filter as well. So in this case, the filter is as if combination between dataset cartography and humans. So that's what we did. And here's some examples that you can see. It's pretty impressive. So Salinger wrote similar letters to other young female writers. Other young female writers received similar letters from Salinger as well. So here you kind of need to be able to flip subject and the rest of the sentence, and you see like there's have, there's sent, some similar thing that GPT-3 did do. And apparently this was some of the important examples to add more of. And there's yet another non-trivial edit to make. So that's that. Now, I haven't told you about the last part of symbolic knowledge distillation yet, but let's begin with the neurologic first, because that portion is dependent on neurologic. So neurologic A** is our new paper at NACL, which actually builds on our previous paper, also at NACL, but previous year, called neurologic decoding. And in this talk, let me just merge them up into one piece. So the quick vision, high-level vision is that, well, we talk about how larger is better in the industry, as well as news media, but the search algorithm, classical search algorithm, is also important. And for example, for the original AlphaGo success, Monte Carlo tree search was really integral part. And so maybe we can reconsider what search can do for us, even in the era of deep neural models. And so that search algorithm or decoding algorithm, people usually don't talk about it very much. They just use a beam search or some sampling, which is not adding very much to the innate capabilities of neural models. But here the idea is that maybe we can add a lot there, such that it can even handle logic constraints given in conjunctive normal forms that we vaguely remember from AI textbook that we once learned. So, by the way, if humans need to deal with this kind of logic constraints, we can do that on the fly. We don't need to look at 10,000 examples to fine-tune ourselves. You can just do it. So that's the idea. Maybe machines should be able to do that too. And you might wonder, I need to redo this whole, okay. So you might wonder what kind of applications we can do. I realize this is one slide with a lot of, oops, I did it again. Yeah, okay, so I was going to say that application-wise, there are a variety of things we can do. Anyway, so neurologic decoding in a nutshell is, in the original version, it's some kind of a search data structure that you need to carefully maintain. Let's not do this because you just ate breakfast and requires too much coffee. I'll just say that the reason why this particular implementation is somewhat complex is because when you are trying to deal with the satisfaction of conjunctive normal forms, which has lots of clauses, you need to track, whether the clauses are satisfied or unsatisfied, and if so, how. Some of this satisfaction is reversible or irreversible, depending on different items inside. So that's why there's a bit of a complexity, and through this search, of course, we're not guaranteed to always satisfy, but that is that. And so that's a quick summary of our previous paper, which is sort of like specialized beam search algorithm for conjunctive normal form satisfaction. Now, let me tell you a little bit about what's the problem with just that. So imagine a very simple task. I ask you to write a sentence including these three words: car, drive, snow. So this is a very simple case of logic constraints. Just include them all. In which case, we might have this conjunctive normal form shown as here, and then maybe we generated this much so far. I drive my car during the, and then what? So as a human, obviously, you want to pick winter because you gotta deal with the snow, and it's easier to deal with the snow when you say winter here. But the problem is conditional probability of summer might be higher, and the previous neurologic decoding only is able to look at the past, so it's not able to project to the future. And so the score function is basically just language model score combined with the clauses that are satisfied or not, and that's not enough. And there's something called the A-star search in the AI textbook, which has been also used successfully in many NLP work. So we're going to do that in this work to add A-star-like heuristics, but it's A-star-esque because with neural language models, it's not easy or impossible to design admissible heuristics. So how we do that exactly, it's not overly important, but I can just tell you that there are different ways of designing heuristics, which may be based on greedy look ahead toward the future, or maybe beam look ahead is a better idea because it's a little bit more informed, or maybe it's more important to worry about diversity, therefore maybe we should do sampling based look ahead. So in our work, we just try all of them and compare. Let me tell you a little bit about what happens with the original neurologic decoding first. So in the common gen data set, which is about making a sentence including a few keywords, and you can imagine that this kind of situation arises when you try to do data to text generation. So this is simplified case. So let's look at coverage. Here, blue is what happens with the typical sig-to-sig models, and here x-axis is model size. So the bigger the better in terms of logical constraint satisfaction. But even the large model didn't really learn to satisfy everything, whereas neurologic, whether supervised or unsupervised, so neurologic can be applied to either off-the-shelf neural language models or on top of supervised sig-to-sig models. Doesn't matter, it just performs well all around. But this is not at the cost of quality of generation. So in terms of Rouge and Meteor, which happen to align with or correlate with human evaluation in this particular data set, again, neurologic just wins over the beam search version. What's striking is that unsupervised model can outperform supervised model if powered with neurologic. So much so that unsupervised smaller network can still outperform supervised larger network. So here, for example, unsupervised, this is smaller model, doing better than the supervised larger model. So we don't hear this kind of a story very often in the media, but maybe we're overlooking the classical algorithmic power, even in the context of today's deep neural models. So in the paper, we report a few or several more evaluation cases, including constrained machine translation, and then data to text generation of various sorts. I think we are also inspired by Lei Li's, I think this is Lei Li's paper, if I remember right, yeah, based on Monte Carlo tree search. So yeah, whenever I work on these decoding algorithms, I realize Lei Li worked on some of them earlier than we did. Okay, so let's go back to the generic induction. So this is coming soon. Generic knowledge is things like birds can fly. And so what we can do is, given a concept like a bicycle, we want to be able to generate, what a bicycle is like. We want to generate a bicycle has 2 wheels, for example. We want to do this out of GPT-2. So remember earlier, I highlighted how horrible GPT-2 is compared to GPT-3. So bad so that it seems like almost, hopeless to go anywhere. But let's just see whether we can still squeeze some lemonade out of it. So because GPT-2 is so bad, and you cannot do prompt engineering with GPT-2 as successfully as GPT-3, what we do is neurologic decoding, which can give some kind of lexicosyntactic constraints to the output so that when you start a sentence with, this is a predefined format about bicycle, so we have these predefined ways of starting a sentence, and then we add the neurologic decoding on top of GPT-2 so that it generates a sentence that, at least on the surface of it, looks like generic statements. It's actually not a very good generic statement, however, because you cannot really read this, but it says basically bicycles are also pedal, which doesn't mean anything. So it says a lot of nonsense. It's a very low quality. But if you don't put neurologic decoding, then it's even worse. So neurologic decoding can tame the model so that things will look better. And of course, we can do what we did earlier, which is generate a lot of bad quality knowledge, and then filter aggressively, really aggressively by various means. In this work, again, we do this multiple iteration, which turns out to be a good idea. Let me just go to the results straight ahead. So there's a knowledge base on generic knowledge called Generics KB. That's based on mining the web. So this is an approach where you wish that somebody happened to say a generic statement in raw text and then try to mine that. It's actually not that easy to do so because we usually don't talk about that kind of stuff. Like, horses have 2 eyes. Who says that? Nobody says that. So because of that, the accuracy is quite low, and also the quantity is not too good. But using GPT-2 is so cheap. Unlike GPT-3, we don't even need to pay for it. So we can really overgenerate. And with the power of neurologic decoding, now accuracy is about 40% good. So when something is 40% good, usually we feel very discouraged, then we don't touch it. But what if we really, really overgenerate and then aggressively filter? See like how aggressively filtered? But the point is that most of the black portion is gone. And then a lot of good stuff got lost, but still the resulting knowledge base is much larger than whatever previously existed, and yet much higher accuracy. But the really exciting part is this one. So GPT-3, compared to GPT-2, powered with neurologic decoding, powered with the symbolic knowledge distillation. What you see here is a precision recall curve. So based on model's own confidence, we can order the generated generic statement and then decide whether we are going to take all of it. So if we take all of it, recall is good, but precision will be lower. But if we remove some of the tail, the worst ones, then you get high precision. So the red is GPT-3, and this is really impressive. Right now, the GPT-3 Instruct, the new version of it, is quite a bit at the around of like 80% good. This is really scary good. When I originally tried this, before they improved Instruct, it was somewhere here. So they definitely did something with our own queries about generic statements and improved it quite a bit already. But fortunately, GPT-2 with neurologic is above that, so that's good. And this is really, when we are doing this, on one hand, we wanted exactly this graph in the end. We wanted to beat GPT-3 with GPT-2. On the other hand, it's really a daunting fight to have, because GPT-2 is just so bad to begin with. But anyhow, so the premise, I'm going to share some closing remarks now. So the premise of this talk still is that scaling laws are real, denial is futile. It's good stuff, really, what GPT-3 can do. Yeah, I mean, I really like, I know that academics usually have a mixed feeling about this kind of papers, but I hated the first one, and then I really liked the second one, and that really changed my mind. Though I want to say that scaling is just probably, I think it's a necessary condition for making AI work. I just said AGI here, but let's just say we don't care about AGI, just AI working better. But still, it's a necessary condition, but not the sufficient condition. But it's a necessary condition. I mean, the fact that it's not sufficient condition also doesn't negate that it may be an important factor. But I don't think we can really, for example, just solve common sense capabilities by scaling things up only because you can't reach it to the moon by making the tallest building in the world 1 inch taller at a time. So about this kind of question, I don't know. I mean, self-driving cars were coming as of, I don't know, several years ago, and then it's still coming and not coming at the same time. And I don't know if it will actually happen within the next 5-10 years. I think there are a lot of really interesting things we can do in academia without large compute, especially because there are just a lot of blind spots. And what I really like about decoding algorithm is that it's really, you don't need to train anything very much. You don't need to do hyperparameter tuning. You only need to worry about the algorithm part, and it's just so much more fun. I want to say something a little bit about this evaluation part. So the current paradigm of deep learning seems to be exactly this. So you do self-supervision on a lot of raw text, and then supervised learning on a lot of exam text. And this is the winning recipe for pretty much all leaderboard, but that recipe fails if evaluation is set up as a generative evaluation, meaning the machine has to generate the answer as opposed to choose one of the 4 given. In real-life situations, it's unreasonable to imagine an oracle will always hand 2 choices or 4 choices to choose from for machines. That just never happens. And so we do need to rethink about how we are doing evaluation. We never trusted this for human when we evaluate humans' capability, by the way. Like, we don't do this for PhD admission, for example, right? And so this doesn't work in the long run, unfortunately. There's something really fundamental about that in terms of what we are hoping AI to learn by doing this. So imagine that you take a deep learning class and professor doesn't teach any lecture. They give you lots of Python code for you to self-supervise yourself on. Maybe not even PyTorch. It's a new programming language that you've never seen before, but professor gives you so many of them. Together with, 4 choice, these exam problems with the correct answer marked. And then you go ahead and learn. You can imagine how that's just like such an inefficient way of learning. So we cannot really learn true concept this way. Even humans cannot learn. Why is it reasonable to expect that machines can do that magically through layers of, transformer layers? So I think it's just impossible. For that reason, I don't think a scale alone is going to really go very far. It cannot really learn concepts reliably. So when we think about this education material, the thing about human intelligence is that we humans invest so much into education material for humans. There's already textbook for deep learning, and then someone else writes yet another one because there should be a better one, right? And then there's a tutorial already, and then someone else has yet another tutorial. Why? Because it really helps humans to learn better. And so we have this way of learning from declarative knowledge, or knowledge that's really written for the purpose of education, in which things are really described for the purpose of teaching. And maybe we need more of that for machines as well. And so in some sense, atomic knowledge graph is that atomic knowledge graph encompasses the kind of declarative statement of a common sense that adult human beings will never tell each other, but we do that for children. Children do ask very simple, straightforward questions because they don't yet know a lot of things about the world, so they ask a lot of why questions, and so that's part of their learning experience. And maybe we need to think more about that kind of learning experience for AI as well, which I consider as the data part that we can also do better in addition to the algorithm. Okay, thank you. Yeah, so, right. So if I understand the question is about the fact that GPT-3 is not even really grounded in this, physical world. So it lacks a lot of other experiences that humans do have. So for that reason, I believe that grounded learning with multimodality and then continual learning that allows you for different types of mode of learning will be very critical for addressing that sort of limitations. Having said that, at the same time, I don't necessarily think that AI should mimic the entire pipeline of human learning, in part because we cannot really recreate the same experience to AI. Like human babies, they really have a caregiver giving care for many, many years before they really start being able to speak fluent language and so forth. So it's hard to completely mimic that, and also AI doesn't really have the kind of a textile and physical embodiment that allows them to go ahead and experiment in the real world. So in that sense, I do think that AI will have to cheat in some sense, and cheat by being able to read a lot of a text, for example. And so it seems that the main challenge is how do we somehow find out the right balance between the two. But yeah, thank you. Yeah, great question. So it's true that this is very reminiscent of active learning. Compared to the traditional active learning for which data set items are already sort of there and then you only need to choose which one to annotate by humans, I personally believe that the new challenge that NLP community face is that we may need to generate data set items. And so in some sense, the data items are there in a very infinite conceptual space, but we don't know where they are. And so we cannot randomly sample them and hope that we somehow hit them randomly. I think being able to actually generate diverse set remains a really challenging research question. So this work was more of our first shot approach. I do believe that if we can systematically really enhance how we find diverse data points that really challenges models to do NLI better, I think that would make a big difference. By the way, I forgot to mention, we have a demo of a Wang Mi model available, meaning Wang Mi's data set, but the model trained on Wang Mi is available online. And we find that for tricky questions, it's really much better than other SOTA models. Maybe wangmi.apps.lnai.org. Yeah. Yeah, so that's also a great question, why the iteration helps. Hand-wavy explanation is that, so when the teacher model generates potentially useful knowledge or data, and then we filter that, although we did the filter so that the filtered version is better portion, the data set still is not as good as it can get yet in terms of diversity or complexity. So then when we train a model, new model, and then start generating data that way, the data becomes overall higher quality. So, we filter it again, but I think it's because the data itself becomes better and better and better over time as you use a stronger generator for the data. Yeah. Yeah, so the question is, what are the tasks that GPT-3 cannot solve? Even for the multiple choice questions, there are quite a few data sets that GPT-3 still cannot, including even social IQA, which is about very simple social common sense problems, and GPT-3 is not very good at that. So we have a new paper at EMNLP about the lack of theory of mind of neural language models. So there are many that it's not very good. I think whether it's good or not has a lot to do with whether the question is asking something that's far off from the surface patterns that the model was exposed to. And I think some people feel like, oh, but GPT-3 knows a lot of common sense, so maybe it's a matter of a scale. I think the gist of common sense in my mind is all about exceptions, and the fact that exceptions are not exceptional in real life. Exceptions are not exceptional in real life in the following sense. Birds can fly. Penguins don't fly, so let's write them down. And so is GPT-3 ready to go? No, because I can come up with a million examples in which birds cannot fly. Sick birds may not be able to fly. Dead bird may not be able to fly. Birds that are just born usually cannot fly. Birds that are in the vacuum, even if it has an oxygen tank, cannot fly. Birds in a cage cannot fly. Birds covered in oil cannot fly. I'm sure that if there's like $1 million bet between you and I, and we keep coming up with exceptions in which birds cannot fly, I'm sure that it can go on and on and on. The weird thing about this is that we never heard these examples, and yet you and I know what the correct answer is, because we have a true understanding about the concept of a bird and the concept of a flying. And I don't think this surface pattern-based approach can do, and we really need we need a method that can really learn concept. And so if your QA is about that, GPT-3 fails at it.
I guess we are running out of time. I'm sure you still have plenty of questions. You can still ask her during the break. So Professor Choi will be here during the day. Thank you for the wonderful talk. That's really MacArthur Genius Award talk. Well, we have another wonderful speaker, Sasha Raj. So maybe you want to set up while I'm introducing. So Sasha Raj is a professor at Cornell University and also a researcher at this very successful startup Hugging Face. Perhaps most of the people in the audience are using some code or examples in Hugging Face. So he has been working a lot on the NLP, in particular natural language generation, these probabilistic deep models, and efficient inference. There's one piece perhaps everyone working on NLP and transformers should read, the annotated transformer. I'm sure most of you have read this web page, really nicely illustrated explanation about transformer. And he's also author of many open source packages. One of them widely used, many of them widely used. One particularly widely used is OpenNMT. And also the MiniConf, the conference platform used heavily in during the COVID. And Sasha is recipient of numerous best paper award, EMLP, NACO, and best demo papers at all NLP conferences, ACR, EMLP, NACO. And amazingly, he got best paper run-up award at VAST. Perhaps some of you don't know, VAST is a top visualization conference. And he got the best paper award in DAC. Well, that's unfamiliar conference. That's a top conference for electronics, chips, circuits, hardware design. Well, I really love to have Sasha to stay for a week to have 10 talks for us. But without further ado, we will listen to text generation from Sasha.
Cool. Hey, everyone. It's wonderful to be out here in Southern California. I think I may win the furthest distance award, which means, well, on dissertation committees, it means it's my responsibility to ask the hardest questions. It's always what I'm told. And in, I guess, very professor fashion, I read a book about surfing before I came out here, so I know all the context. I'm going to talk today about some work on model criticism for long-form text generation. This is work from my student, Yuntian Deng, who's on the job market this year. So I heard you guys are looking for 100 new NLP professors. So I offer him up. Cool. So if you know my work, I'm kind of more on the probabilistic side of things. And I'm often very interested in diving deep into the model architecture. It's a kind of funny problem to have these days, which is that I don't have access to GPT-3. And we're beginning to get access to open source versions, but most of this talk will be about GPT-2. Take that as you may. I think there's fair caveats to be said that there's a big difference between those two models, but I still think there's a lot we don't understand about GPT-2. And if I'm being honest, there's still a lot we don't understand about BERT. So I do hope to see kind of more research even on these models in coming years. Goes without saying that language models are extremely fluent. You asked a model to generate something, it will generate something that looks great. The kind of focus of this talk, though, is that it's not totally clear to me whether language models have high-level coherence. So we talk about kind of coherence, kind of referring to one phenomena of many that we would call kind of discourse phenomena in NLP. It refers to kind of how the document is constructed, how higher-level relationships occur in the document itself. The kind of running example for this talk will be a specific discourse phenomena, which is section headers. So we're kind of imagining here that we're generating from GPT-2 size models. It generates a Wikipedia article, and we're just going to have it ramble, so just let it go. And at no point will it make any kind of mistake in the sense of producing a sentence that couldn't have been maybe written by a human. But if we look at the kind of higher level structure of what came out and kind of reverse try to infer what the sections it wanted to write about were, we get kind of high-level versions of some phenomena that we used to see at a low level. So in particular, one thing you'll see is that it will generate a background, and then it will just generate a background again, right? So it'll just kind of reset itself, get stuck in a loop, and just generate a completely fine background, but do it twice. So this talk is kind of about that idea of what these kind of high-level mistakes look like and how we can quantify them. So what I want to do is I want to give probabilistic measures for thinking about high-level coherence. And what I'd like is to note that perplexity seems to have been fantastic. I mean, we used to argue about whether perplexity really corresponded to fluency, but I think it's really held out that perplexity just turned out to be a great measure. But I'm a little more skeptical that we figured out exactly the right measure for high-level structural properties. And I don't think this talk is the answer, and a lot of people in this room have proposed kind of great alternatives to this. But I think this area of trying to kind of figure out how we should measure this, this phenomena is pretty fascinating. So that's what the talk's going to be about today. And I'm going to start with a kind of very simple experiment. This is kind of just a simplest idea that I could come up with of how to represent the section problem in a kind of smaller, more controlled environment. So the way it works is I'm going to make a synthetic language that has kind of section dynamics. It's going to kind of generate a bunch of characters, and then it's going to generate a separator symbol. And the rules of this language is that there's some randomness in terms of what character comes next, but there's a deterministic mapping from these sequence of characters to some kind of high-level section marker. So I know that PBWMS represents the green section. And if it's helpful to think about this probabilistically, this will come from a hidden semi-Markov model. Here, the sections are these latent variable z's, and the actual text we're observing is autoregressively generated within each of these sections. So if I make this data, and then I tell you that I can go backwards to the data before, then I can say I have a kind of deterministic posterior relationship. I can take some generated text of any form, and I can infer back what the actual sections were of the underlying data. Cool. So the thing I'll note is that if I train a language model, here I'll just use language model to refer to a transformer, on this data, it basically figures it out. It gets basically the optimal perplexity. It fully figures out exactly how to generate each of the next symbols in the process itself. And in fact, it does roughly as well as if I had told it the true generative process. So optimal is kind of the entropy of the language. Language model is what it fits when we give it the surface form. And HSMM is if I tell it the true model class, I tell it the generative procedure of the underlying data, how well could it do? So for all kind of senses, it really learned this language and got an extremely good perplexity. But I think what I'm really interested when I talk about these problems is how do we quantify how good it got the underlying phenomena? did it really get how this data was generated? Did it figure out that all I was doing was kind of switching colors and then generating data IID from these colors? So the way we're going to do that is we're going to use a kind of statistical technique inspired by some Bayesian reasoning approaches called model criticism in latent space. And the way it works is the following, and I'm going to show this graph throughout the talk, so I'll linger on this for a bit, is that we're going to sample data from some unknown model. We're then going to run some sort of posterior inference to guess what the underlying phenomena was in that space. Now, I'm not going to assume that I can kind of magically get what this inference procedure is. I'm going to basically pick some known inference procedures that maybe not perfect, but like they seem natural or they seem like they should work. And then I'm going to kind of compare how these two things matched in this latent space. So we're going to think about how we captured the underlying phenomena just by looking at how it modeled this z variable. So in this case here, we can, even in the synthetic case, create, I think, what is kind of a disturbing property. If I deterministically infer what the latent sections were for the language model, it actually does quite poorly. It makes a lot of mistakes in terms of actually generating good section transitions. And I can quantify how far it was from the true distributions that we would have gotten from the underlying known model. So in this latent perplexity, kind of a perplexity in latent space, we actually seem to be quite far. And this isn't so crazy. It seems likely that the sections represent a relatively minor amount of perplexity. But if you miss the sections, for a lot of problems, you've kind of missed the whole point, right? You've kind of captured the surface transitions, but you haven't picked up the underlying structure. Now, not that it's saying it should have or needed to, just that this can be bothersome in some cases. Cool. So the kind of assertion here is that the LM fit the surface distribution, but missed out on these high-level transitions. And it's quite possible that these important phenomena may be worth relatively few bits in terms of perplexity. So at a GPT-2 scale, maybe we're not capturing them, and we might just not be missing them in our data structure. So what I'm going to do in this talk is I'm going to try to quantify these properties for some specific cases in NLP. So I'm going to go back to kind of relatively classical models in natural language processing. I'm going to use this technique, I'm going to apply it to a model, and try to understand whether these long-form discourse properties have been captured. In particular, the question is, does this really happen? Am I kind of picking up on a synthetic kind of phenomena, or am I describing something that we see in practice? So let's look first at this idea of section coherence. So to run this experiment, we're going to critique the discourse coherence of a model generating articles. So this is exactly the phenomena I talked about at the beginning of this talk. We're going to have the model kind of just generate text, and we're going to try to infer back what the section titles are. Now, unlike in the case before, where I controlled the whole generative process so I knew the true answer, here I don't really know what the section titles actually are, but I'm going to posit that we're really good at this kind of classification. So I basically can assume a model that sees the data and not the section titles can basically at 100% accuracy figure out if we're in the background section or if we're in the personal life section of a Wikipedia article. So even if I don't know the true generative process, I basically can now assume that models are really good at that. So what I'm going to do is I'm going to sample from a language model. We're not going to have explicit section headers. We're just going to do this by kind of using the actual words the model says. We're going to use a classifier to invert this process to map us to our latent space Z. And then we're going to compare the transition probabilities in the implied section model that we've produced. And we can compare these quantitatively to understand how far we were from the true assumed process. Now, in practice, we can get the true process because we can just count how often section transitions occur in real data. So to run this, we're just going to run with two kind of middle-sized models. We run with GPT-2 of various sizes and GPT-Neo, just to kind of give a different language model. We're going to run on various different sorts of document classes that have this kind of high-level section behavior, Wikipedia, Archive, and PubMed. And for all these models, we're going to run with a relatively long window, so it doesn't really come up so much in practice. And we're going to hide the kind of actual section names from the model itself. So the kind of main observation we see is that perplexity doesn't really correspond to latent perplexity on this task. We find that both models get extremely good perplexity on this data set, but that kind of a small kind of decrease in perplexity, at least on the right side, can lead to a large change in this latent perplexity. So at least on Wikipedia, we saw that GPT-2 does relatively well on latent perplexity, but GPT-Neo does kind of extremely poorly on this task. For other data sets, we see this correlation even go in opposite directions. So in this case, for PubMed, GPT-Neo has a better perplexity, but seemingly worse at kind of capturing the high-level structure or the high-level changes in the data itself. And similar results for Archive. Now, one of the things that was most interesting is that we found that even when you kind of change the model scale, this correlation continues not to hold up. So we went from small to XL on GPT-2. The underlying perplexity of the data gets better, but we don't see a major change in the latent perplexity. So the things that are getting better at this scale seem to be mostly phenomena about fluency, and we're still kind of missing out on some of the high-level structures of the sections or kind of long-term changes in the data itself. Cool. I'm going to skip this section for time. I'll get back to that. One neat thing about this approach is that we can look at the underlying actual distribution table that we get out of the approach itself. So for Wikipedia, there actually aren't that many sections or transitions that you might see. And this approach allows us to compare the probability of transitioning in the true model from the probability of transitioning in the implied model that we induced from GPT-2. So in particular, we can look at the particular mistakes the model tends to make. A lot of these are self-loops, so repeating section information like background or description. But we also see other phenomena like ending too early or kind of switching between sections in the wrong order. And I think for instance, the switch between background and personal life kind of makes sense. And if those are kind of similar phenomena, you get a kind of self-loop style behavior. Cool. So another thing we did is we compared this approach to human judgment. And in particular, what we're looking at in this graph is correlation. So the correlation here of perplexity is in blue. And we see that we don't really get a clear correlation of coherence and perplexity generally. Our approach here is shown in green, and it correlates better between the two models itself. We also compared to an approach called MAUVE, which I'll talk about later in the talk, and the authors are all in this room. So MAUVE is kind of another approach to this idea that doesn't require specifying a model directly, but instead kind of utilizes the data itself. And MAUVE also shows a relatively good correlation between these two phenomena. Great. So the next phenomenon we looked at was co-reference. Co-reference is one of my kind of favorite phenomena of language. I just think it's extremely interesting, and it's a extremely cool kind of thing that language can do. So given a sentence like Lisa runs off to find him and they kiss passionately, afterwards Josh tells her the reason why he's going to their first gig and that Lisa is going to do it too. Not a great sentence, but the kind of thing that GPT-2 will generate. We can, with extremely high accuracy, kind of infer what the co-reference relationships are in this kind of quote story. We can kind of label these with these colors. So each of these colors represents a co-reference cluster. Here I use a subscript to represent which cluster it is, and a color to represent that these are within the same cluster itself. When I look at a particular word in this generation, like the word Lisa, I can look back at all the previous co-reference relations we've seen. So in particular, here is this last relation, and I can look back all in time to see all the previous mentions that were made in the document and which entities they refer to. Now, in order to apply this approach to co-reference, what we're going to do is we're going to reduce things a bit to some of their features. So we're going to reduce them to gender, number, whether they're nominal or pronominal in this setting. So in particular, I can say, what's the probability of female coming up after male, her, he, their? So you can think about this as a language model in reference space. So it's a language model of like what sorts of references you might make next. And the kind of assertion is that there is a natural way when a human writes a story, how they reference things. Like there are certain patterns that people are used to, and then there are certain patterns that look sort of weird, right? Like one of the reasons why this sentence looks so weird to you is that even though it's fluent, it makes kind of very complex, ambiguous references kind of casually throughout the setting. Cool. And so we can do this to kind of get a quantitative sense of how far it is from kind of the assumed nature of reference. So the setup here is that we're going to sample from the language model. We're going to infer using co-reference. And then we are going to compare on basically a simple 5-gram language model of the co-reference chains to understand how they work in practice. So what we find is kind of at a high level, almost all the models at this scale are doing pretty poorly. They don't really match the phenomena of co-reference that you'd see with a human writer, and that this doesn't really seem to be getting better with scale, again, with the caveat that it's at this size. Again, one of the cool things about this model is that we can extract the kind of the mistakes that you would see in practice and kind of the issues that the model might see. These are a little hard to read, so I won't get into them too much, but I think you guys have all kind of played with these models, and you get a sense of what this is. Like, they'll kind of introduce a bunch of things into scope, and then it kind of randomly seems to choose one to refer to, or kind of refer to things kind of constantly by a nominal form, even though a human would then kind of use a pronoun instead. So let's look at some examples. So here's one. Okay, after their marriage. Okay, these are going to be hard to read. Let's see, what's the best way to think about it? I think you have this thing here, and he also tells him that Raja Rao is his father. So it's not wrong. I mean, all of these things can refer to something. It's just that it's not the way someone trying to make text non-ambiguous would use pronouns, right? That there are too many of them and they're used in a particular way. And you can kind of see this even in a 5-gram language model, that the probability of using he after having another different reference in scope and then having 2 other pronouns also nearby is just, even in a 5-gram language model, you can get a sense that that's not something that should have high probability. Cool. So we have a bunch of these in the paper that go through and analyze a bunch of different examples, but I'll move on to the last part. So the last thing we looked at was topicality. I'm not sure whether topics are kind of often thought of as fully discourse phenomena or some combination of two, but there's something that you can talk about at least at a document level. So in particular, we're going to look at topic correlations. So not just what topic a document is, but the correlations between two topics within a document. So this is like saying something like, I don't know, maybe sports and, sorry, let's see, Olympics and wrestling might be two things that will often correlate showing up in a document. So to do this, we're going to sample from language model. We're going to use a correlated topic model to try to infer the latent space. And then we're going to compare the topic distributions in this model. And what we find is that for this phenomena, language models just kill it. They're like so good. We basically get perfect matching with the data that we see. And I think this graph really shows it pretty well. So this is a matrix of correlated topics that you would see kind of just in documents themselves. And we extract the correlated topics from the generated data. And it's just basically a perfect match. For comparison, we show what PubMed would be on the right. And at least at this level, whatever the kind of statistical phenomena that is going on in terms of correlated topics, knowing what to talk about or what topics belong together, that just is like totally nailed. It's not meant to be a kind of critique generally of these approaches, just a kind of method to show what they can do and what they can't in practice. Cool. So I want to talk about some related work just because a lot of folks in this room have done awesome stuff in this space. So I mentioned MAUV, which kind of presents a way of thinking about this problem that doesn't require kind of specifying a linguistic process underlying the data and can kind of provide a generic way of looking at kind of long-form evaluation. Lots of people over the last year have talked about this phenomena of language models having poor discourse, and people talk about it using different languages or different means. Language models can refer to non-existent entities, they can do it incorrectly and incoherently, and they can fail to maintain character identity. So these are all kind of, I think, different folks describing kind of similar phenomena in similar ways. I also mentioned that a lot of people have been doing really cool stuff to actually improve these approaches and actually kind of build in ways to get around some of the issues they have. I think this idea of kind of first coming up with a plan and then kind of filling in the details seems extremely promising. Although it's also plausible that, I don't know, GPT-5 will kind of resolve these issues once the kind of low-hanging perplexity kind of gets sucked up into the model itself. Cool. But again, awesome work from folks in this room. So generally, I want to kind of say that this is a version of model checking. It's a nice statistical property for utilizing, or for checking kind of properties of models. I think this is a generically really valuable technique that I think could be used more widely for different properties in NLP, and people should know. And that specifically what we show is that language models seem pretty good at some statistical phenomena, but seem to kind of be lacking in others. And it's worth thinking about how to make them improve in these means. So thank you very much, and I'll stop for questions.
Good talk, Sasha. Really like this stuff. Quick question. So this seems like a problem with the language modeling loss in some sense. Is there a way to think about this latent PPL as a loss during self-supervision? Yes.
Yeah, it's a great question. I think you can absolutely do that. I'm a little hesitant to. I'm not sure I want to build notions of like coherence and section coherence into our losses, just because it's nice that Perplexity doesn't know anything about linguistics in some way. So I'd like to have losses that kind of do it generically or do it in kind of more of an information theoretic way than ones that kind of require specifying these things. But at least for evaluation, I don't mind kind of specifying some properties I'd like to see. Yeah.
Hey, Sasha, cool talk. You don't want to adjust the law, so where do you want to put your money in terms of what's going to be the change, do you think, that's going to, if there is, that's going to enable ability for things like co-reference model architecture, just data size,
Yeah.
different laws?
Yeah, it's a good question. I have a lot of trouble answering this question because I don't have access to POM. It's a funny problem, I would say. Like, I don't feel comfortable making a bet because I don't know how InstructGPT works, and I don't have access to POM. So I don't know, I'm pretty agnostic at the moment. I'm glad I don't have the problem that Yijin mentioned of having to tell reporters what I think about. Although I tell Twitter all the time. But what do I think in practice? It's all interesting. I mean, it's fantastic to see what's happening, but I'm not sure I believe kind of chain of thought yet as a solution. And the results that come out of Google, some seem mixed, some seem really positive, and it's hard to know without actually playing with it.
Hi, and I have a question about the conclusion you have about the large language models can do well on topic modeling, but do bad on the co-reference. And this brought me into thinking about is it related to the frequency modeling of transformer on long inputs? Because there are some recent works on examining the modeling capacity of transformer on extremely long inputs. Do you think it's related?
Yeah, I mean, I think they're very related. I think there's two things. One is kind of capacity, and the other is kind of usage of that signal. So one is a question of whether it could, and the other question is, does it, or does it pick up on that? Let's see. I don't think this is the kind of thing that gets solved by kind of messing with attention in that way. But the question of whether it gets solved with scale or not is open.
For the sake of time, we probably should end the Q&A session now, but our break will start, so you can still ask your questions. Thank you again, Sasha, for the wonderful talk. 11.
Please work, please work. Okay.
Yeah, it's working.
Okay. I want to do the extend desktop thing. So. Oh, I see. Ah. Okay. So I need the slides to be on this screen. Right. Yeah, so how do I do this? I'm going to extend my screen, but I want my notes. So, let me see.
You should, yeah.
Okay. I am. Okay. Can I go to the screen? Looking for. Oh, there you go. Where is it? There you go. Okay. This is it. And then what I want to do is play. So, okay, my notes are here. Okay. Excellent. I think. Yeah. So I can play. Okay. I should work.
Yes.
Okay.
I was scared there for a second because it was displaying like.
And the notes
Yeah.
were out there. Yeah, that was, yeah. Yeah. But it's awesome. Okay. Thank you.
Earlier, like, I like to spend time with my daughter, but it was like a duty rather than fun, right? Like, I should be doing this kind of thing, right? But now at this age, it's like, yeah, I want to get over it. Right now, you're just like having fun with her, daughter, yeah. Like playing games, reading books, drawing, whatever. Are you the first guy?
Second time. Drive, get here safely. Oh yeah, same.
I mean, it's actually, it's a little bit weird. I might actually, because when I joined this college, and AI2 has this incubator, so the understanding was that I'll be good. So I've been mostly not doing that. But now, what it is, it's not the CEO.
I'm always talking about.
But there's a split completely between AI2
They were like,
Hello, everyone. Our second section is about to start. I know the break. Everyone enjoy the break. You want to plug in? We're missing half of the. Let me try to grab people. We're missing half of the audience.
你记得给我举时间牌哈。
我一定给你举，放心。Hello, everyone. Let's get seated, please. Hello, welcome back to the second morning session of the SoCal NLP. In this section, we have two very exciting talks. So the first ones come from Professor Yanning Shen from UC Irvine. Professor Shen, she is an assistant professor from UC Irvine, and her research are primarily focused on machine learning, network science, and signal processing. She graduated from her PhD from University of Minnesota, and she also got a numerous reward from her research, which including the, sorry, I usually don't read, but since she has so many awards, I don't want to miss anything. So including the, where we should start, the EECS, Rising Star Award from Stanford, and also she received the University of Minnesota Doctoral Dissertation Fellowship, the Microsoft Academic Grant Award for AI Research, the Google Research Scholar Awards, the Hillman Fellowship in 2022. So she also is the nominee of the MIT Technology Review Innovators Under 35 Asian Pacific in 2022. And today she's bringing us a very interesting talk on fairness-aware graph neural networks. Without further ado, let's welcome her.
Hello, everyone. Thank you very much for the introduction, and thank you very much for having me here. So today my talk is about fairness-aware graph neural networks. And I'm probably one of the persons who knows the least about NLP in this room, because I just started learning about it after I was invited to this talk. I said I have to learn about this so that I can actually tell something that is useful. However, apparently 1 month is not enough to learning all the details, so I will still try to connect what I will be talking about in this talk with some potential NLP applications, but please take it with a grain of salt, and if you have any ideas, I'm sure you have better ideas, please feel free to share with me. And let's get started. So since this talk, I'm going to talk about graph neural networks. And the reason that we are specifically interested in graph neural networks is because, of course, graphs are everywhere, including social networks, brain networks, and also from the talk in the morning, I understand that knowledge graph is also widely used in NLP. So graphs are mathematical structures to model pairwise relations, and with nodes can denote, for example, in flight networks, it can denote flights in flight networks or neurons in brain networks or accounts in social networks. And edges can denote the flight paths between airports, neurons connections in brains. They are always come with also nodal features, so which can denote whether in airports and type of neurons. So let me clarify that my research and this talk, all the motivation are actually obtained from social networks. So, but later we will also see some potential application in NLP. So here is my the results of my learning. So graphs, as far as I know, has also been used in NLP, where nodes can be sentences and age can be similarity scores between sentences. Nodal feature can be sentence embeddings. Or it can denote the triplets in sentences, and edge can denote, be links between subject and the predictive. And the nodal features can be word embeddings. Okay. So, what is graph neural network, and why is it important? Graph neural networks, by its name, we know that the input is not only like numerical or Euclidean distance features, but also graph structures. So it has been shown to achieve state-of-art results for several tasks over graphs. And the main idea of a graph neural network that is different from conventional neural network is it is trying to aggregate information coming from neighbors via neural networks. Okay, so here's an illustration. Basically, you're given a graph. Instead of how this graph is come into picture for the neural network, is the graph structure determines how you aggregate representations in each layer. Okay, for NLP, this is a necessarily incomplete literature review that GNNs has been also shown effective for relation extraction, question answering, summarization, machine translation, and abusive language detection. So now, another keyword of my talk is fairness. So why are we interested in fairness? Because there's a bias. Okay, so let me give you some background about bias in machine learning. We actually already know that machine learning algorithms may lead to biased results. What it means is that it may lead to results that are unfair to certain underrepresented groups. Examples are different error rates for face recognition algorithms. Like we show that face recognition, it is shown that face recognition algorithm results in much better recognition accuracy for male faces, and different crime prediction rates based on ethnicity, as well as credit card approval rates based on gender. Okay, so this is critical for various applications and the policy making. And there has been extensive literature on bias reduction in machine learning, but on non-graph data, while fairness over graphs are relatively underexplored. And here's some background on possible bias in NLP. So basically, the reason is that the performance gap, there exists a certain type of performance gap between groups with different sensitive attributes. So it leads to bias that assigns stereotype correlation with respect to sensitive attributes. And it has been shown that NLP models propagate a bias within the training data. For example, word embeddings attribute computer science field to male, tends to attribute computer science field to male. And there's also one so-called Wall Street Journal effect, which shows that certain model perform better on language written by middle-aged white men. Okay, and henceforth, this all shows that these type of bias also exist in NLP-related applications, and it may affect the critical real-world decisions such as job application, which are okay. So now, let's go one step further. We know that bias exists in machine learning and bias exists in potential NLP. And how about bias in graphs? So you may ask me, since we have extensive studies on bias in machine learning. Why do you care about graphs? What is the special challenge for bias in learning over graphs? The reason is because that learning over graphs actually potentially amplifies already existing bias in the feature vectors because of the structural information there. Okay? Because when we are learning over graphs, we take into account the information from two sources, feature vectors and the structural information. However, it has been shown that we know that nodes, for example, in social networks, tend to link with each other in associative manner, meaning that we tend to make friends with people who are similar to each other. Henceforth, it usually leads to highly unbalanced connections between among users with same sensitive attributes such as gender or ethnicity than among users with different sensitive attributes. While graph neural network, as we said, is trying to aggregate information from neighbors. Henceforth, it leads to indirect use of sensitive attributes in training. Okay? And the fairness is comparably underexplored in graph domain, and there has been recent works showing that indeed learning over graphs may amplify already existing bias, and methods has been developed. However, most of them are designed for very specific learning tasks or frameworks and lack rigorous analysis. Okay? So in this talk, I'm going to specifically talk about efficient bias mitigation techniques that can be readily employed in various GNN-based frameworks, including fairness-aware normalization layer for GNN, as well as attention network layer design. Okay, so now I'm trying to make some connection with NLP. Through incomplete literature review, I realized that most of existing fair NLP solutions are typically post-processing operations, meaning that they first learn the embedding and try to decorrelate the learned embedding with sensitive attributes. Okay? Here are some existing works. And however, the challenge here is post-processing. While it's when it is trying to decorrelate the learned representation with the sensitive attributes, it is shown that the actual effect of representation biasing is hiding the bias, not removing it. Okay. So in this talk, I'm going to briefly introduce two techniques that can be used for in-processing. And we also have work on pre-processing, but due to the limit of time, I will not have time to cover that. Okay, so let's look at how representations are learned via graph neural networks. Since I'm originally come from a very signal processing background, so I tend to answer this question by, instead of first running experiments, I want to ask, can we explain why the source come into picture? Okay, what is the correct measure of the bias? So let's first look at the graph neural network structure here. Okay, this is a mathematical equation, and I defined this notation, but let's first ignore that, and let's look at what this mathematical equation is actually talking about. Okay, basically, given our input graph neural network in each layer, what it is trying to do is to aggregate information from the neighboring nodes. Okay, so in illustration, it can be seen here that, for example, node A, when we try to learn representation, how we use the graph structure is aggregating the information from its neighbors, B, D, and C. B, D, and C. Okay, so, and this is specifically an example of a mean average, taking the average of the nodal features from neighboring nodes. And we can see that in case when the graph actually have bias, meaning that let's consider these green and blue nodes are female and male, okay? And we can see that if in a social network, female tends to have more female friend, male tends to have more male friend, then the graph neural network will learn a representation where in each layer it is aggregating information from nodes that are from the same sensitive group. Okay, so if the nodal feature indeed entails a certain kind of bias, then through this aggregation framework, the bias will be amplified. Okay, so how are we going to characterize this and solve this? So now comes a little bit of math. So what we are trying to answer is, through this aggregation framework, how can we measure the result, the correlation between the aggregated representation and the sensitive attributes? Okay. So henceforth, we try to find a bound for the rho where is the total correlation between the learned aggregated representation and the sensitive attributes, and we bounded it through certain terms. Okay, let's look at some terms. So first is this delta. Delta is the mu0 minus mu1, where mu are the average of the representations from nodes in different sensitive group. So what it means is that the average, the mean of the representation matters. The second term is this delta. Okay? The delta is the maximum deviation of the representation. Okay? So which says that how far it is distributed from the center matters. Of course, we also see this G1 and G2, and they are topology-related terms. Since I'm focusing on representation-related terms in this talk, so I did not explain them. So then from this theoretical analysis, we say that, okay, since my entire goal is, remember that when we said that there are post-processing schemes try to decorrelate the embeddings with the sensitive attributes. So now can we enhance fairness by reducing this fairness-related terms, this correlation in the learning procedure? So specifically, we developed some graph augmentation scheme for graph topologies to reduce the topology-related terms, which I will not cover in this talk. And the reason is because I noticed that in NLP, usually the graph is predefined, and we are usually do not modify it, but I may be wrong. And also, another approach is we can change the distribution of the hidden representation to reduce the representation-related terms, which are the discrepancy in terms of mean and the maximum deviation. So here comes the first idea is we can change the group-wise distribution via learnable parameters by adding a normalization layer and can efficiently reduce the bias-related terms. So in order to do this, we were inspired by the batch normalization schemes that were widely used in training neural networks and has been shown to accelerate the optimization in training. And similarly, GNNs also suffer from slow convergence rate and instability issues. And existing work have shown that graph norm to operate this type of adding this type of normalization layers in graph neural network also helps with the convergence. Okay, please note that here these gamma, alpha, beta are all learnable parameters. So it's not something that we calculated from the data. So now the key idea is, since I want to kind of manipulate the distribution of the representation in the learning procedure, so I should apply this normalization layer instead of for the entire graph, should apply it in a group-wise manner. okay? So that I can manipulate the mean and the variance for each group and then try to bring them closer, okay? So now, in order to bring them together, obviously, I use some regularizers, add to the original objective function, so hopefully while learning, these obtained mean and maximum deviation can be smaller. And these regularizers can be expressed in terms of trainable normalization layer parameters. Okay, so you can see that what we need to do is to add this normalization layer and add the regularizer to the original learning task, and then train the neural network. Okay. About the convergence. Okay. Well, it has been shown that doing this batch normalization really helps with the convergence of the training. However, the challenge here is now if we apply a group-wise normalization, then it renders the convergence unclear because we are separate the nodes into different groups and apply a normalization layer for each group. So luckily, we can still prove that using this fair normalization layer, it achieves probably faster convergence than in the case when no normalization is used. So it provides probably faster convergence while taking into account the fairness. Let's see some experimental results, and here's these are. As I mentioned, that we carry out experiments in social networks, and these are widely used fairness-aware measures to measure what is the performance of fairness enhancement, including statistical parity and equal opportunity, which is trying to characterize the difference of performance of different groups. And here's the result. So note that these deltas should be the lower the better. And we can see using fair norm, it can indeed achieve much better fairness measure, while at the same time, the accuracy is not influenced much. And here is numerical results to show the training convergence. And we can see that this experiment result indeed validate our convergence analysis, that by using fair norm, it still can achieve better convergence rate than when no normalization is used, which is this red curve is no normalization is used. Okay, so let me do a quick summary on this topic. The fair norm is a unified normalization-based framework to both to reduce bias and improve GNN convergence. And we show theoretical analysis for fast convergence. And we show experimental results. And so some potential NLP application is, I will just go through this quickly to give you some food for thought, but take it with a grain of salt. So we noticed that GNNs has been used in relation extraction. Specifically, the graphs used is the dependency trees, and it has been shown it can capture a long-term relation between words, and the GNN creates efficient solution. So one example would be, instead of using existing framework, we can easily insert a fair norm layer as an in-processing fairness tool. Okay, I will not go into details. And similarly for question answering, here I will skip this example. And I want to quickly go through the graph attention neural network. Previously, we see that a graph neural network is trying to do average or concatenation of representation between nodes, while attention network is trying to learn different weights, give different level of importance to different neighbors of the nodes. So it can be used to select the most relevant neighbors and generalize the averaging and maximum polling in representation of the neighbors in the original GNN. Okay, so now we want to answer the questions that when we are averaging, we are necessarily paying more attention to one neighbor compared with the other. So when we want to pay attention, what if this attention has a certain type of bias? Then it may even amplify the bias. So henceforth, let me skip this slide and look at these results quickly. So what we can see, this is the general attention framework. What it is trying to do is trying to learn the attention alpha IJs for each neighbor. Okay, and then these alpha IJs will be used for later aggregation of the node representation. So now of course, we start from some theoretical analysis saying that through this attention layer, will it lead to more correlation in the learned representation with the sensitive attributes. So again, we analyzed the total correlation between the learned representation of a GAT with the sensitive attributes, and here's the bound. Okay. Here specifically, I want to talk about this alpha chi, is attention for inter-edges, and alpha omega are the attention for intra-edges for nodes from different sensitive group. Okay, and specifically the total attention is sum up to 1, and this is a topology-related term that I will not focus on. So now we can see that indeed the analysis shows that using a graph attention network, these terms is how much attention we pay to neighbors from same sensitive group and different sensitive group matters. So now the question is, if this is the bound, then can we design an attention mechanism so that we are aware of such bias that are resulted from the attention mechanism? So let's focus on this alpha terms related to alpha that tells us how to design attention. So since this is an important term, so what we do is we solve an optimization problem to minimize this term, hopefully, so that subject to the given constraint. So that in this way, we can reduce the total correlation of the total correlation between the representation and the sensitive group. So now, luckily, it has a closed form solution, and this guides us on how we should actually design fair attention mechanism. Okay, so there's a little bit of math, but on the high level, let me show you. On the high level, what this mechanism is saying is that the analysis shows us if we have a different number of neighbors from different sensitive group, like female, male, then what we should do is somehow balance out the attention we pay to different sensitive group. Okay, so this is a high level idea, but it is supported by math. Okay, so here's some experiments on social networks, and the model is a 2-layer GAT, graph attention networks. And again, we tested the fairness metric, and we show that the fair GAT instead indeed can improve the fairness matrix of the original graph attention networks with similar utility. Okay. Potential NLP application. I have to emphasize its potential. That we did some literature review and seen that attention has been used for this relation extraction. So and it has been shown that GNNs create efficient solutions by being able to pull in information over a large number of dependency structure in parallel. So here. We looked into it, and the existing framework in this specific paper, they were not directly using GAT. They are using attention plus GCN. So we were expecting if there's using GAT and a fair GAT, then it will be able to improve will be able to improve the fairness and possibly even the utility. Okay, so let me conclude. Here we provided theoretical analysis for source of bias over graph neural networks and the graph attention networks. And we show design of fair GAT and fair known based on theoretical analysis, which incurs small additional computational complexity and experiments on real data sets. Specifically, I want to mention that it is applicable as an in-processing fairness tool together with other processing, pre-processing or post-processing techniques, and hopefully for NLP as well. That concludes my talk. Thank you very much. And here are the some related papers. Any questions?
Thank you very much for the wonderful talk. Any questions? All right. Here you go.
Yeah, thanks, Professor Shen, for your talk. I think, so in natural language processing, the embeddings are usually trained in an unsupervised way, but the GNNs are usually trained towards a specific downstream task, right? So what if here we have this case, we just have a graph, but we don't have labels for the nodes. We want to learn, just learn fair embeddings for a general purpose, with not specific to this node classification task. Do you have any thoughts on that?
I see. Excellent question. So first of all, it's good to learn that NLP usually is trained in unsupervised way. Secondly, for your question, actually GNN can be trained in unsupervised way through graph contrastive learning. And in addition, you may want to also check out this paper that is fairness-aware graph contrastive learning, which exactly develop a contrastive learning-based fairness-aware graph neural network. So what it is trying to do is using kind of, I'm not sure whether you are familiar with contrastive learning, so it is generating different augmentations and trying to learn through the contrasting the different views. So graph neural network can also be used in that way. So without label is not a problem in this sense. Does that answer your question?
Any other questions? Questions? Yeah, maybe I can ask a question. So there's multiple tasks for graph type of data, like say node classification, edge detections, or even graph level prediction task. So how these algorithms, like your normalization or attention layers, gonna because I saw you give a quick result on node classifications.
Yes.
So how these kind of algorithm mitigates the bias for other graph prediction tasks?
I see.
Or whether that's generally applicable to these tasks?
So short answer is yes, it will be applicable, because as you can see that through the design in this framework, we have never talked about what are the ensuing tasks. We are looking at data distribution and how we pay attention to different sensitive group. It is the schemes that we talked about here was not directly relevant to utility. That also allows us to use it in unsupervised manner and in a versatile way for different learning tasks. What we needed to do is, for example, add a normalization layer in the learning task wherever we use a graph neural network and use the original training mechanism. So yeah, or modify the attention mechanism in the original graph neural network. Does that make sense?
Thank you.
Hi, thanks for the wonderful talk. I agree that, in-process treatment may be more likely to debias the bias fundamentally. But the challenge is that nowadays, everything, not everything, a lot of things are about pre-trained models, large-scale pre-trained models, and we don't have the computational power and the access to the large-scale data. So is there, any middle ground between in-process treatment and post-process treatment?
I see. So thank you for the question. You are absolutely right that for post-processing usually can be readily used for whatever we have already obtained, right? And is more computational, possibly more desirable. What I think that this in-processing can be used is that, for example, for the normalization layers, that we can use it in each and every layer. But once we analyze how the representation distribution influences the bias, it can also be used as a post-processing, right? And also that it does not mean that we need to make the changes in each and every layer in the original trend model. We can certainly do some type of transfer learning and only fine-pruning the final couple of layers.
Mm-hmm. Thank you.
Thank you. That's a great question.
Let's thank the speaker again. While our speaker set up, let me give a quick introduction. So we're very excited to have Professor Swapha Swapyaptita. I apologize if I pronounce your name incorrectly. I really tried my best. And Swapha, she's an assistant professor from University Southern California. And her research interests are mainly in machine learning and natural language processing. Recently, she has been focusing on various interesting research topics, including assessment data sets qualities, finding semi-automatic algorithm that collecting high impactful and high quality data, and also investigating how human bias that playing a role in data set collections as well as model learning. And of course, she has received numerous research awards, including the Best Paper Award of ICML 2022, the Best Paper Award from NeurIPS 2021, as well as the honorable mention, Best Paper honorable mention from ACL 2020. And today, she's bringing us a very interesting talk on generating data sets for robust generalization. Let's welcome her.
Thank you for the introduction. I'm so thrilled to be part of the SoCal NLP group. I'm a new professor here, just started in fall of this year, and very, very thrilled to be part of this really large community now. So in the morning, we saw some skepticism about the state of NLP. Everyone is talking about GPT-3 and what can we do? GPT-3 seems good, not good enough. How do we talk to journalists and so on? But for me, I feel very thrilled right now to be doing NLP. You can see that all these applications that we use almost on a daily basis have some component, have some language component to them. And at the center of all these applications, there is some ability to process human language at scale. And so what a thrilling time to be involved in this research. Let's just soak that in for a second. And yes, we all know that progress in NLP has tracked closely with the ability of large language models, such as GPT-3, to learn from vast amounts of unlabeled data. But I'm pretty sure everyone here who has played around with GPT-3 also knows that it may not always be reliable. So for building reliable and trustworthy applications, we still need a large amount of fine-tuning of these language models, and that still requires labeled data. So in this talk, I will bring together these two concepts of language models as well as large labeled data set collections and see how we can merge these two worlds together. And speaking of labeled data sets, I'll start with a very popular one based on the natural language inference task, where given a premise, such as the sentence, "A dog is chasing birds on the shore of the ocean," the task is to predict whether a hypothesis, which is another sentence, "The birds are being chased by a cat," is true, false, or neither. So as you can see, this is a simple case of a contradiction. Now, this task was popularized through the introduction of two large-scale data sets, the Stanford NLI and the multi-genre NLI, multi-NLI data sets, which together contain about 1 million crowdsourced instances. And this data size was not seen too much in NLP before the introduction of these data sets. And truly, these data sets have been responsible for a ton of interest in this task. As you can see from this leaderboard taken from March of this year that reports accuracy in NLI, you can see that models are now beating the performance of even humans. So this should give us a little bit of a pause, but let's come back to that later. But the bottom line is that there has been a ton of progress with the introduction of pre-trained language models. But if you look closely at some other examples, especially the predictions given by state-of-the-art models, we'll see that for simple sentences which talk about similar phenomena about, dogs and cats, the middle one talks about a dog and cat are snuggling up during a nap. Does this mean that dogs and cats rarely, if ever, snuggle? Can't say, right? So it should be a neutral. But if you look at the predictions of these state-of-the-art language pre-trained models, we see that they tend to get these examples incorrect. So this is somewhat surprising as well as underwhelming. Now, to understand what is going on here, a few years ago, we ran a very simple experiment to study this phenomenon. So what we did is we removed the premise from the task. So the task is somewhat nonsensical now to humans, given nothing. We have to now predict whether a hypothesis is true, false, or neither. That doesn't make too much sense. However, the model continues to make exactly the same prediction in each of these cases. Now, on a closer look, we saw that this might be happening because each of these examples, each of these hypotheses, contains the mention of the word cat. And it just so happens that the SNLI data set contains a disproportionate amount of cat examples, which are contradictions. So the way this happened is because the SNLI data set contains premises which were collected as captions from the Flickr data set. And annotators were tasked with writing contradictory hypotheses for these captions. And because those captions had a lot of talked about a lot of dogs, because Flickr has a lot of dog images, what annotators did to write contradictions is simply replace the dogs with cats. So we have a lot of contradictory cats. So this is an example of a spurious correlation that the model picked up on to make its decision. And even very powerful models are subject to such spurious biases. Now, in order to make sure that our models are making the right decisions because of the right reasons and not because of some spurious biases, we need to really look at this interaction between the model and individual data instances. In other words, we want to understand how can we better analyze the model-data relationship. And this goes beyond what simple aggregate measures such as accuracy can really offer. So to answer this, we consider the model training dynamics. We propose a 2D or 3D visualization which plots individual data instances in the context of other instances from the same data set. On the y-axis, we consider confidence, which is the mean probability of the true class aggregated over E epochs of training. On the x-axis, we considered variability, which is the standard deviation with respect to the same true class probability, again, across E epochs of training. And for cleaner visualization, we also consider correctness, which is a coarser variant of the confidence metric, which simply records the ratio at which the model predictions match the true class. So with respect to these three metrics, this is what the SNLI data set looks like for the Roberta model. Now, you might remember this from the talk earlier this morning by Yejin, and I'll try to give more details on what's happening here, but Yejin did make my life much easier, as she always does. All right. So as you can see, there are these very clear regions in the data map. In this talk, I will only focus on one of the regions, which you see on the right-hand side, where the instances have high variability, or in other words, the model keeps on changing its decision about those instances through the course of training. So given this phenomena, we call these instances ambiguous with respect to the model. Now, to study this region more carefully, we trained a model selectively on just this part of the data set. We consider a third of the data set from the ambiguous region of the entire data set and compared it to the original model, which is trained on the full data set. So we want to not only see how this region, or a model trained on this region, performs on the original SNLI test set, that is in distribution performance, but we also look at a variety of challenge sets which are created independently of the SNLI data creation process. And these challenge sets are out of distribution with respect to the original SNLI or multi-NLI data sets. All right, so if you look at the performance, we see that compared to a model that is trained on all the data, a model trained on just this ambiguous third of the data does much better out of distribution, while the in-distribution accuracy is retained. So this indicates that ambiguous instances might really be responsible for the performance gains that we see in these state-of-the-art models. So perhaps less can be more. Now, moreover, we saw that these ambiguous instances contain very interesting phenomena. So here you have a premise and expression gathered there that I can only describe as half puzzled and half relieved. And the hypothesis is that the expression on their face was puzzled and relieved. So is an expression that is half puzzled and half relieved the same as an expression that is puzzled and relieved? The model tends to oscillate between neutral and entailment. And indeed, lots of humans also tend to not be entirely sure what the label should be. This is an important property of these ambiguous instances. Now that we know that not all training instances contribute equally to model learning, and especially that instances in this ambiguous region seem to be rather valuable for learning, the next question is, how can we use this information? This is the question we set out to ask in the first part of my talk. Can we leverage the data maps to improve data set collection? And again, we saw a little bit of a teaser of this Wandley data set, but I'll go into the details of how this was done from the perspective of collecting data or generating data. All right, so spoiler alert, and not really, because you know this, compared to a multi-NLI, which is 4 times larger, models trained on Wandley do much better out of distribution. And these magnitudes that we saw for Wandley are pretty rare, even for the very popular natural language inference task, which is pretty awesome. So how did we achieve this? So the key idea we experimented with here was to overpopulate the data set with examples which are similar to those that we see in the ambiguous region. Now, one way to do this is to hire some annotators and have them write examples that are similar to the examples we see here. However, given that we know these cat contradiction or like changing cat to dog kinds of heuristics that annotators seem to follow, we were very skeptical that annotators will be able to do a good job. So this is where GPT-3 came in handy, and especially we realized that we can modify GPT-3 generations in interesting ways by controlling the hyperparameters and so on, although we can't really train GPT-3. So this made GPT-3 a good choice for over-generating ambiguous instances. So how did we do that? So we start with an ambiguous example from say, multi-NLI, and this is with respect to Roberta, which still seems to be one of the best performing models on this data set. So in this case, this example talks about some kind of set relationship. So 5% probability that each part will be defect-free, and the hypothesis is each part has a 95% of having a defect. So this is the seed ambiguous example we start with from multi-NLI. Then we find the nearest neighbors of this particular instance from the rest of the multi-NLI data set. Note that these nearest neighbors won't be nearest neighbors in the data map. These are nearest neighbors with respect to some high dimensional embedding. And finally, we provide GPT-3 an instruction to write a pair of sentences that have the same relationship. In this case, this is an entailment relationship, and we just send this to GPT-3. And GPT-3 does pretty well. Based on this prompt, it generates an entirely new example, which again has the same kind of relationship, also about set complements. So that's great. So it generates something like 1% of the seats were vacant. That means 99% of the seats were occupied. Awesome. But if I play around with GPT-3 a little bit, it will generate something like about 1,000 people are diagnosed with something, and the hypothesis is about 9,000 people are not diagnosed with the same thing, which kind of makes you think it assumes some universe of 10,000 people, 1,000 people have something, and the rest don't, which is not great. It uses some assumption that is not immediately clear. It could also generate something entirely different. He has never smoked and he doesn't drink. And the implication here is that he has smoked and he has drank, which is not even an entailment relationship. And this is absolutely not what we want. So what can we do? Given that these GPT-3 generations are not reliable. So we use a simple filtration strategy to get the instances that we want the model to get the most out of. And since we ultimately care about overpopulating or overgenerating these ambiguous instances, we go back to the variability metric we saw earlier in the talk from data maps. So which is the standard deviation of the true class probability. But the catch here is that we don't have a true class. We just generated a piece of text. So to overcome that, we come up with an approximation that involves a max probability. So this is an expected worst case ambiguity. All right, so this is our filtration metric, and we'll retain the examples which have the highest max variability. We still have one part of the puzzle that's missing, which is labels. And labels are particularly important because, remember, we wanted reliable and trustworthy data sets. So in this part of the process, we will bring back the human annotators. And we, for all these filter generations, we get 2 annotations per instance, and that's what we include in the data set. All right, so this completes the entire reasoning for why we adopted this pipeline. And like you learned earlier, Wanli actually translates to 10,000 reasoning, which is something Alyssa, who's a fluent Chinese speaker, told me, which is pretty neat. Wanli has 100K examples. So one key difference between our data set and the seed data set multi-NLI is that Wanli is not label balanced. We have many more neutrals than entailments or contradictions. So we found that this corresponds to the more, to the more natural distribution of most of the examples we came across. All right, and so for the burning question, how does Wanli do on these examples? Does it have the same spurious biases? Turns out that it does better than the original multi-NLI model. Obviously, this is just a few examples, but we provide much more empirical results on these hypothesis only bias kinds of artifact prevention in the paper. All right, and to look at another example from Wanli, here you have the premise as a result of a disaster. The city was rebuilt, and it's now one of the most beautiful cities in the world. And you have this hypothesis, the disaster made the city better. You can think about it a little bit. Our annotators seem to think that this could either be an entailment or a neutral or a contradiction. So these are very interesting phenomena we saw for Wanli. There is a lot of human ambiguity, and this is an exciting direction of future work that we have already started building on. All right. So this was the pipeline. We saw this, all well and good. Maybe we can do this for every data set. It's not ideal because, again, it involves this very expensive GPT-3 model, and we saw earlier that maybe we should look at smaller models. We need to do some kind of model distillation in a clever way. But the second part, which I believe is the key motivation for the rest of this talk, is that the generations we got were challenging compared to the entire collection of multi-NLI, the data set. So these are globally challenging examples. But such a large data set is not easily available. So what can we do? How can we do better? So can we generate data sets cheaply that contain locally challenging examples for models? And this concept of local challenge will become clear in the next part of my talk. And so this is another paper that was accepted to NLP findings, where we look at neurocounterfactuals, where we go beyond minimum edit counterfactuals for richer data augmentation. So consider a couple of reviews. The first is for a movie, and the second is for a game. Now, most humans would agree that the first is a positive review, and the second is not. However, for a model, these decisions might look quite different, most likely because they rely on the presence of certain words, good or better, in the review, while missing the higher level semantics that is necessary to figure out the sentiment. Now, while these are not exactly the kind of spurious correlations we saw before, these are still useful features, but still, over-reliance on these simple lexical features might lead to incorrect decisions. Indeed, typical classifiers are trained to distinguish between positive and negative sentiment based on a few examples. However, a real-world data distribution might contain similar examples corresponding to a much more complex true decision boundary. Now, such examples could be counterfactuals of the original examples, which contain changes that alter the label while still retaining key concepts in the original example. So counterfactuals are based on the principle of causality, which states that the relationship between the target sentiment label here and its direct causal ancestors remains invariant. So intervening on the causal features causes the label to be flipped. So the key idea here is that if we were to augment our training data with these counterfactuals, the task models could learn a more accurate decision boundary. So the central question I'm interested in answering is, how can we create counterfactuals automatically? So to do that, let's go back to the review we just saw. Here, this is a game review. The motorcycle is the better part of the game, but I have little else to say. So it's not a very positive review. Now, if one was to consider better as the key sentiment-bearing word here, one could write a counterfactual that simply replaces the word better with worse. But that doesn't quite achieve what we are looking for, because the review still reads, the motorcycle is the worst part of the game, but have little else to say. It's not great, right? Now, you could consider simply removing the word better. The motorcycle is the part of the game, but I have little else to say. This is nonsensical. Similarly, introducing positive sentiment-bearing adjectives like awesome or I'm so thrilled do not have the same connotation as a positive review. In fact, the review might still feel a little disconnected. What might work, though, is incorporating many of the changes together, which don't quite map to just a simple insertion, deletion, or substitution. So let's look at this example. The best part of the game is the motorcycle chase sequence. What an absolute thrill. So this seems like an overwhelmingly positive review, and we are interested in going beyond these minimal edits to create the style of somewhat loose counterfactuals. All right, so to be precise, the reason this review in yellow works is because, first, it retains the key concepts in the original sentence or the original review, that is motorcycle and part of the game. It changes the parts that alter the sentiment label. So, but I have little to say becomes what an absolute thrill. And thirdly, and this I'll argue is the key thing here, is it introduces new concepts that add context and really help improve the naturalness of the review. So motorcycle becomes a motorcycle chase sequence. I don't play games, but I'm guessing a lot of these games don't have static pictures of motorcycles. It's usually some kind of like riding a motorcycle, I guess, like how fast you can go, something like that. I don't know. But yeah, that's what makes the review, more natural and positive. All right, so to enable the later of the two objectives, we will rely on something called language model steering, and this is a very simple thing to do. So you start with a GPT-2 model, and you continue pre-training it on positive reviews here from the Stanford Sentiment Tree Bank, and you will end up with a positively steered GPT-2. Analogously, we can obtain a negatively steered GPT-2 by continued training on these negative reviews. So this steered language model handles the part that will change the label by introducing more positive words, as well as it will use the ability of GPT-2 to introduce new concepts. All right, so to retain the key concepts in the original, we need to follow two steps. First, we need to extract the concepts, and we do this by mapping the concepts, concept nodes in ConceptNet to spans in the original review using a method called CocoaX. Now, once extracted, these concepts now need to be in the new counterfactual. Here again, we use neurologic decoding, which you saw earlier. Thank you, Yejun. So this is an algorithm, a control generation algorithm that enforces lexical constraint through the modification of beam search. And the clauses, the constraints are specified as clauses in conjunctive normal form, as you can see in orange there. So the overall objective looks like this. The first term corresponds to an autoregressive language modeling objective, and the second term is the one that enforces these lexical constraints, which correspond to spans in the original review that we wish to retain. So another key element of our generation is the selection of a prompt for language generation. And in this case, we use the longest sentiment neutral prefix in the original review that does not include any extracted concept words. So far, what we have done to generate this new review is to use a language model that has access to some reviews in a single sentiment polarity, as well as this constrained decoding algorithm, no extra data. So to summarize the whole process, you start with the original review. which happens to be a negative review. You extract concepts from the review. Here, the concepts are movie, collection, analogies, plot, and devices. We restricted ourselves to nominal concepts because that seemed to work the best. Now, because our original review was negative, we use a positively steered language model. Here it is GPT-2 fine-tuned on SST2. And the extracted concepts now go into our constrained decoding algorithm, which when applied on the positively steered language model results in what we call a neurocounterfactual, because neurologic, it's based on neurologic. In our experiments, we will compare augmenting a training data set with these neurocounterfactuals as opposed to minimal edit counterfactuals, which typically only change the sentiment-bearing adjectives. So as a baseline, we will augment the minimal edit counterfactuals to the original training data, and we'll also create a data set that augments these neurocounterfactuals to the original and compare the two. So as prior approaches have worked on different kinds of minimal edit counterfactual data augmentation, some of the authors are actually in this crowd. But we compare with both automatic as well as manual ways for incorporating these minimal edits into the counterfactuals. So our extrinsic evaluation involves testing on various in-domain and out-of-domain test sets, some of which contain human written counterfactuals, such as CAD from Kaushik and co-authors, as well as contrast sets from Matt Gardner and co-authors. And we'll also check performance on out-of-domain test sets for generalization. Our intrinsic evaluation metrics will contain several measures that look at the diversity of the generations compared to the original review, the fluency of the generations, as well as the sentiment. So compared to a setting that has no data augmentation, just the regular training data, and this training data is the IMDb training data, baseline minimal edit counterfactuals tend to improve performance. And these are shown in gray and green here. Our neurocounterfactuals improve performance further across multiple settings, bridging the gap between no training data augmentation and training data augmentation with human written counterfactuals. Surprisingly, in some of the cases, neurocounterfactuals even exceed the performance of augmenting with human written counterfactuals, which is pretty cool. One important case here is the leftmost result, which is on the IMDb test set, which is the in-domain test set performance. And that is low across different counterfactual augmentation approaches because models tend to over-rely on those simple lexical features that we saw in the beginning that help them do well in domain. And so we see similar trends when we control for the augmentation size, where we augment the same amount of data across every setting. So here are examples of some neurocounterfactuals. As you can see, they're very naturalistic. The scenery, the music, and the theater are all top-notch. This is something I would say if I was to review and if I was tasteful. At the same time, first of all, we look at the diversity of these counterfactuals compared to the original. Here you see that you do get more diverse generations. At the same time, the perplexity tends to also be lower on the generated neurocounterfactuals, showing that fluency is not affected. And again, you saw in Sasha's talk that fluency tends to correlate pretty well with perplexity even now. So this is to say that neurocounterfactuals are much more diverse while still maintaining fluency. We also see that neurocounterfactuals are better at sentiment steering. So compared to the baseline methods, neurocounterfactuals tend to do better on their own on the sentiment classification task, which kind of shows that an off-the-shelf sentiment classifier is able to say that the new counterfactual actually steered the sentiment. And we also saw that as we increase the number of neurocounterfactuals in the training data, you keep on getting better out-of-domain performance. Putting all of this together, we see that generating locally challenging instances via controlled decoding with smaller language models can result in these counterfactuals. And we also saw that globally challenging instances can be generated by a collaboration of humans and models. So why generate data sets? Because creating data sets manually can be very expensive and can really slow down the entire research process. So this is a very good way to accelerate progress. And the second thing is that you can focus on the data quality explicitly over just data quantity, which I hope by now you're convinced that scale isn't everything. Thank you. Take questions.
Thank you very much for the wonderful talk. So given the time constraint, maybe we can take two questions.
Yeah, I understand what you're asking. So we didn't try that because, so in some prior work, we saw that just, sentiment steering, like not using any constraint decoding, just giving the context as like a negative review and training like, doing generation with respect to a positively steered language model does pretty much that. Sometimes the exact words might not be steered. Are you asking like if you keep the sentiment words the same, but you're switching the context? Okay, yeah, so that is not something we tried, but yeah, I can see something like that working as well. But I think like the whole concept of this counterfactual is like you either change these causal features or you keep the causal features intact and change everything else. So we can try different combinations. We just didn't do this and that work.
Hi, thank you very much for the great talk. And I have a question about the curious, ambiguous examples. Like you used an example before about half puzzled and half relieved. So are those examples like ambiguous to model? Are they also ambiguous to human? Is there any human evaluation about the consistency between these two?
Yeah, that's a great question. So in our paper, we saw that this actually correlates with kind of the human ambiguity. And we measure human ambiguity by like how the humans disagree with each other. Although there is not like, so sometimes the humans tend to, so if you remember the data map, some of the examples which were in the right-hand side, ambiguous examples, also corresponded to things that humans found ambiguous, but also instances which were in the hard-to-learn region, which the model keeps on getting wrong every time, also were ambiguous to humans. So those were the correlations we saw. But things which are easy to the model are also easy for humans, which is neat.
Thank you very much. I have a very quick follow-up. So if an example is ambiguous to model A, have you tried, like, say, the consistency of this? Like, what if you change the base model for model B, let's say Robota versus BERT or DBOTA, something like that?
Yeah, so when models are very close to each other, for instance, BERT and Robota are pretty much the same architecture with like some changes in hyperparameters and so on, then you see a big overlap between what is ambiguous to BERT and what is ambiguous to Robota. Again, these terms, ambiguous, hard to learn, these are tools for understanding what's happening in the data as opposed to like hard and fast rules that, okay, this instance is ambiguous because, it had a certain probability. I think looking at the training dynamics metrics themselves is more illuminating in those cases. But in general, yeah, if the architectures are similar, the models struggle on similar examples.
All right, I'm sorry, Michael. Given the time constraint, we can ask her a question during the lunch break. Let's thank the speaker again. So I think we have lunch outside, and we will come back around 1 o'clock. Thank you.
So real quick, as you're going out for lunch, please take advantage of this chance to network and don't just sit with your lab. Space out, meet new people, especially you UCSB people. I'll be very mad if there's a UCSB NLP only table. I will come and yell at you. So space out. Okay, everyone, 10 more minutes for this poster session, and then we'll be switching into poster session 2. So last chance, check out all the posters you want to see, and then we're switching up. 10 more minutes.
¿Da cuánto lontano?
All right, it's time to switch to poster session 2. So if you're in poster session 1, start wrapping up your conversation, taking your posters down, and at 2:40 we'll officially start session 2. So start wrapping up. Thanks, guys. Testing, 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 testing. Can you hear me? All right. So you think if we just went on to the talk, you think everyone would be able to hear in this condition? Is it too loud? Okay, can I have everyone's attention, please? So, yeah, sorry, we had an unconventional poster session extension cause, but now I think it's time to wrap up the poster session, and let's get into the last couple of talks. So yeah, please, hello? All right, everyone, please wrap up your conversations and come sit down. And also, please try to pack in, compress the seats as much as possible. We had some people standing in the last session, so hopefully everyone can get a seat. Thank you.
Okay, please get seated so we can start the last session. All right, so I think we should go ahead and start it. Welcome to the last session of the SoCal NLP 2022. As a tradition in the natural language processing community, one thing we want to do is to actually learn, right, from other communities and actually, really try to mutually inspire each other. And over the last few years, there's so many, interactions between computer vision and the natural language processing community, including, transformer from NLP to computer vision and a lot of recent development in text-to-image models. So it is really my great pleasure today to introduce our invited speaker, Bole Zhou. So Bole is right now assistant professor at UCLA in the computer science department. And before that, he was assistant professor at the Chinese University of Hong Kong. And before that, he was a PhD student at MIT. So he did a lot of wonderful work in, really pushing the state of the art in computer vision, right? So I think it's a really good opportunity for us to, understand more about, the synergies in these two fields and see, how we can work together, right, to push the field forward. So Bole today, he's gonna talk about human-AI interaction via emergent learning. So Bole, please.
Okay. So the intuitive way to use it just have this moving human just drag and drop this head up. Then we can generate, ideally we want to generate some image like this. Then sometimes we may change the pose of the cat, then move the head on the right a little bit. Then we want to achieve this more intuitive, like human just click on the image and move the things we want. So that is a ideal or more intuitive way to create contents. So we have this recent CVPR work that try to improve the spatial editing capabilities for the image generation. So we want to leverage the emergent control capabilities of the model. So for the generators, we design some the spatial key points as inductive BIOS to include in the generation process. Then to supervise this spatial key point, then we utilize the spatial attention of the discriminator. You know, here we still work on the GAN. So in the GAN, distinguish whether it's a real or fake image. So we utilize the self-attention from the discriminator to guide this key point, because from this interpretable machine learning study, so we can generate a heat map to visualize which this discriminator is paying attention to. So it turns out this discriminator pay more attention to the cat head locations. So we can use this as a self-supervision to our spatial points that we can train our inductive BIOS in the generator. So after training, then we have this very nice interface to control the generation process. So here is a demo showing you that we have this generated cat. Then user can simply drag this key point. Then we can control the location of the cat, where we want to put the cat. We have also multiple levels of key points to have more fine-grained tooling about the result, like this middle level editing, so we can fix the locations and change the settle, like the shape of the ear a little bit. So here is another demo result that we use this technique to edit the building scenes, the outdoor building scenes. So user can use this intuitive dragging or spatial control to generate a location they want. So that gives human more control on this generation process. So human can better convince their intention and preference to the model to generate the things we want. There was this kind of human controllable or human configurable image generation. So more ideal case will be giving this generator. It would be great to have some human interface, right? It's like a digital camera and a lot of parameter. Each parameter corresponds to some numbers or attributes for the output image, such as a focal length or those attributes. So it would be great to have some interface that allow people to control the things we want. So to achieve this goal, so we developed some method that try to do unsupervised discovering of the emerging concept. So giving this trained model that's used for image generation, we developed some this unsupervised discovery method that can discover the components, the principal components in the activation. So each component then is aligned with certain attributes. So based on the discovered component, then we build another interface. So each, right now here, each slider bar corresponds to the component terms. Then user can just change or drag the slider bar and control certain attributes. So one very interesting property here is those components are just unsupervised discovered. So we don't have this predefined dictionary. So those are just figured out by the model itself. We even can control the pose of this 2D characters, which means this pose is some implicit attributes for this image creation. So this allows a user to have more control on the generation process. So that greatly facilitates this human-AI interaction to make the generative model to generate the things we want. Also, we don't have this language prior here. So after we do this discovery, we just show those results to some Amazon Mechanical Turk, then we can collect the annotation for each slider bar. So that is the unsupervised discovery of the this emergent concept. So that leads to the main topic of today's talk. So I think this kind of human-AI interaction, so emergent learning is a very promising directions. So we try to use this model to train on some primary task. Then we can look into their internal representations and see how those internal representations align with our human knowledge or human dictionary. Then we can utilize those discovered or allied concepts back into the model and better understand the model, or we can interact with the model to generate the things we want. So we have been doing this kind of emergent learning or studies for quite a time. So actually one of my earliest PhD work, so I was, many of you, as a PhD student, as many of you, so I've done this work, object detectors emerge from recognizing things. So that is actually one of my favorite works. So we train this neural network to predict the scene category of the image. So it's just the image classification task. The training data we have, just the scene label, like set of living room image, set of bedroom image, then we train this model to recognize that. So it turns out the internal units emerge as object detectors to detect a lot of interesting concepts inside the image, such as detecting foods, bookcase, or car, roads inside the image. Those detectors are interesting because they are just the emergent concept detector that without the same explicit supervision. The supervision we have is just the scene classification supervision. So they are not like semi-supervised learning, they are not unsupervised learning, they are also not supervised learning. I call it emergent learning because it's just the emerged concept inside the model that try to solve the primal task. Later, we further developed some method called network dissection that try to automatically quantify this emergent concept. Basically, this network dissection works. We just input the image, then we can record the activation. Then we just align this activation with a dictionary we collected. So in computer vision, we have a lot of the object detection or semantic segmentation data sets. So we can just align with annotation. So we can discover a bunch of interpretable units or emergent concepts that align with the unit activation, such as we have object parts, materials, and textures. So here, this histogram shows all the emergent concepts from solving this recognition task. Later, then we have some recent work that try to look into the model trained from reinforcement learning. So that is even more interesting, right? So we have, nowadays reinforcement learning is very widely used to solve a lot of tasks. So you train this neural network to solve this, let's say this local motion task. Then we get this local motion representation. Then we try to analyze what have been learned inside this model. So if we can associate some kinematic attributes with those internal activations, so that will lead to very cool applications. For example, here, if we can, for this learned locomotion agent, so it's just trained to walk forward, then if we can associate some attributes, such as some unit may control how to roll the body, or some unit will control how to move left, move right, or how to move their left or right leg. Then we can have this kind of very interesting human-AI shared control application. Previously this agent just do this very boring moving forward task. Right now we can have human in the loop. Then each keyboard right now correspond to certain activated regions. Then user can click the button. Then we can activate and deactivate those modules and control the behavior of this agent. You can see here we want this agent move left, then we press a key, and then this agent will stop there. Then we also can ask this agent to spinning around. So through this kind of analysis, so we can have more controllable and steerable agents. So that can facilitate this human AI shared control or human AI collaborations, which is a very promising future direction. So how we did this? So we have a paper at the NeurIPS. So we develop a method called policy dissection. So from the name, you can see it's a follow-up work for our network dissection, right? So we extend this network dissection ideas to analyze the policy representations. Basically, what we are doing here is we get this pre-trained local motion agent. So we just do a lot of rollout. Then we can collect their kinematic attributes. For example, here, some kinematic attributes correspond to the heating or the yard rates or some velocity. So we also can go into the internal representation and record the activations for those parts. Then very naive next step is just doing this time series analysis. So we can have this kind of frequency matching, try to match the unit activations with output kinematic attributes. So that then we can annotate those internal units. So each internal activations will align with certain attribute, kinematic attributes. So from that, then we can control the behavior of the agent by activating or deactivating the unit that corresponds to that attribute. For example, we can deceleration, or we can make this agent spinning. It's more just increase the yard rates. Also move up, then just move this by x velocity. So here is a result that we apply the policy dissection to a bipedal robot. So this is a robot just doing very boring task, right? We just train this agent to do this move forward task in some virtual environment. So this is a bipedal walker just trained to move forward. So it's a very boring primary task. Then we apply our policy dissection to those agents. Then we can discover many interesting skills. Here we call it motion primitives. So here I list 6 motion primitives that emerge from solving this primal locomotion task. And then you can see this agent, we can actually have this crunch or turn left, or even have this very amazing back flipping skills. So those are the skills that emerge inside the representation in order to solve this primal locomotion task. So with this kind of discovered skill, then we can have this very nice human AI shared control in new environments. So here is in testing environments, then we have totally new environment that's quite different to the primal training environment. So in this testing environment, it's more like a parkour environment, a lot of obstacles. Then we can have user in the loop to press a key. Then we can more like issue some order or some commands to the agent. Then the agent can execute those commands and finish this very challenging task. So you can see this testing environment is very different to our training environment. So there is a very high domain gap between the two. So here another one, we use this to overcome this, to improve this test time generalization. So here is some lagged robot. So at the beginning of the training, this agent, or after training, this agent can just walking forward, right? So it's a very simple task. Then after we train this, then we deploy this agent to some new test environment with some obstacle. Then the agent cannot solve this task because it's not trained to avoid this obstacle. Then we apply the policy dissection, then have our human in the loop. Then human can work with the agent to achieve this navigation task in this complex environment. You can see here, user can press a key, then issue some order, then the agent will execute the orders. Sometimes you stop, then avoid, overcome these obstacles. So this kind of human AI shared control allow this agent to have this generalization across environment. So we evaluate this kind of test time generalization. For example, here is the results. If we just train this agent in this environment without obstacle, so the reward is very high. So if we directly deploy this agent in the new test environment, then the performance drops significantly because they are not trained to avoid this obstacle. If we can have this human in the loop control in the test environment, then we can recover those scores. Then the scores, which means this hybrid human AI system can solve this test task. If we just retrain this agent in the test environment, then they can have this 445. So this human AI hybrid system already get to the more performers that can, for the agent that train in the environment. So I'm pretty excited about this kind of human AI interaction with emergent learning, right? So the foundation or the essential here is to discover this actionable knowledge inside the representations. Then this agent, this AI models will learn a lot of AI knowledge. So we call it an AI knowledge. We also can have human knowledge, right? So those two knowledges are not actually perfect alike. So that is actually interesting part. So our previous work just working on this domain is more about working on the overlap between human knowledge and the AI knowledge. But I think what is more interesting is this non-overlapped part. Those are future work, I will say. It's more like a knowledge acquisition. So there are already some recent work try to move into those domains, try to discover this AI knowledge that is not overlap with human knowledge. Those are some new knowledge discovered by AI. For example, here is a recent paper from DeepMind just 1 week ago, published at PNAS. So they work on this acquisition of chat knowledge in the AlphaZero. This is interesting because they train this AlphaZero without any pre-training on human knowledge. But this AlphaZero can outperform our best Go players, which means this AI model should discover a lot of this Go knowledge and as well as some new Go knowledge. If human players can go back and learn from the agent, they can improve their skills. So that will be very exciting future directions. Even in this NLP domain, I noticed there is a work that some emergent linguistic structures inside the model trained from self-supervision. So the highlight here is this self-supervision, which means you just have a lot of noisy data, and then you just train some large language model on this unlabeled data. Then you go inside the model and try to discover this linguistic or semantic or interpretable structures. Then there are perfect alignment between the two. Okay, so I would like to stop here. So I hope, so from this short talk, I can convince you that this human AI interaction with emergent learning will be very interesting directions. So I hope there will be more work in this NLP to discover this knowledge that learned inside the AI models you trained. So I will stop here. So I'm happy to answer any questions you may have. Thank you.
We have time for questions.
Thank you for the super exciting talk, especially the connection to potentially for AI to acquire knowledge in the future that humans do not know. So it sounds like based on the work that you presented, we are taking a trained AI model and we're separating the knowledge and we allow human to control it. But how do you think we can potentially make AIs become cognizant of these structures that could be controlled by humans? And if we can make that controlled by humans, maybe the AIs could use that to control itself. What do you think that will be possible with maybe future technologies?
So you mean when we design the model, we include this controllable structure?
So somehow for the model to become aware. I mean, I'm sorry for the connection to consciousness, but somehow for the model to be able to use some of these structures consistently.
Yeah, I think that's a very interesting direction. If we can, when we design the model, if we can embed some human knowledge inside this neural networks through some maybe symbolic structure or some relation or some physics inside the models, and that actually will help the AI models to learn the things. It's more like building some common ground that we can better exchange and communicate with the AI models we trained.
Thank you.
Thank you for the great talk. This was really exciting in terms of definitely like how can we apply that to, for example, controllable text generation and so on as well. One thing that you may already have talked about, but I missed. So to identify these factors or different aspects of control, one idea that you said about was like using humans, asking humans to annotate what is the slider talking about, for example. But also, can you think of a way to automate that in some way? For example, if you, I would imagine it's very easy to train classifiers to say, for example, which direction is this robot going, right? And so just by like by visualizing the model or the robot acting, there could be a classifier that says this is going left, and then that's something that you can use to identify what the slider is doing and so on.
Yeah, that's a great question. So I think there are already some follow-up work on this network dissection that they use some large language model to generate the explanation for this individual unit. So in that case, so we don't have to use a human to look at this unit to see what this unit is doing. So we can use a large language model to translate this internal activation into some language that we can understand. So it's more like we use this model as the interface to communicate or understand this internal model. So I think that work is done by MIT Jacob Andrew. So you can take a look at his paper.
For the sake of time, we have to move on, but let's thank Bole again for this wonderful talk. All right, so it's time for the last keynote, and I'll have to be the person to introduce the next speaker. I'll do the standard introduction. I'll tell you a little bit about other stories too. So the standard introduction is that William Cohen is a principal scientist at Google Brain right now, and he has a very long and established career in both machine learning, natural language processing, graduate from Rutgers, and then move on to AT&T Research. Did a lot of wonderful work in the early days about rule learning, about other stuff, and then he moved on to Wisdom Lab, before he went to CMU as a faculty member for many, many years. And of course, he produced, many students, and one of them is standing right now in front of you. And then, he does things I would say very different from other researchers, because I can share the story with you. It was 1 year I was his TA for the large-scale machine learning course, and we're teaching MapReduce at the time, right? And there's a language every student needs to learn. It's called Pig, and it was very ugly because Pig was actually written in a way that is similar to SQL. So I was just complaining because I was the TA. But what happened with William Cohen is that he actually rewrite the whole thing. He wrote his new language. It's called Guinea Pig. You can still download it in Python, right? So it almost feels to me that normal people like me, I just do my research. But he would first invent the programming language first, and then formulate the problem in machine learning, and then solve the problem. So That's why I think he's such a remarkable person, and then I've learned so much from him during my years working with him. But without further ado, we're here to hear about his new work about memory is the second most important thing, language models that retrieve. Let's welcome William Cohen.
So thanks so much for the introduction. It's really nice of the organizers to invite me out here. This has been a great day, a lot of wonderful talks. I've forgotten how much fun it is to be at like a small conference in an area that you're really interested in. So let me go ahead and jump in with a little bit of a look back in history. So 40 years ago, this paper came out. And this was before people would put an example in figure 1, but you can see there in blue over there on the side what this paper was about. You get a kind of complicated question, and it would turn that question into Prolog so it could then execute it on a database. So this came out 40 years ago. The system was called Chat80, so it was even a little bit longer ago that this work was done. And this basic vision of a system where there would be a human that would ask a complex question, then some sort of AI system that would come back and give the answer, that's something that, interestingly enough, we're still working on today, 40 years later. Of course, the way we do it is very different. So 40 years ago, that AI system was something that would be hand engineered. So there'd be people that would be involved in figuring out exactly what they had to put in it. So these are supposed to be Fernando Pereira and David Warren, I guess. That didn't persist. So sometime in the last 40 years, so this paper is about 25 years ago, and this is on learning to do the same task. This was a paper by Ray Mooney, and one of the outgrowths of this paper was a new data set called GeoQueries, which is still used today as a benchmark for semantic parsing. Engineering has now been replaced with learning, and here the learning is from pairs, where you've got a natural language sentence and then a semantic parse of that, a structured query against the database. So we've replaced engineering by learning, okay? But importantly, the kind of knowledge that you're representing is quite similar, okay? The knowledge is still these modular components, facts in a knowledge base, and there's something very attractive about that formulation. So these facts can be verified independently, and they can be combined to answer complex questions. And that notion of what knowledge is or should be is something that has also persisted for a very long time. So even in 2018, with this paper on answering complex questions, introducing the complex web questions data set, there was this emphasis on answering questions that are compositionally defined. And again, this is a very compelling picture, right? So nobody's ever written down the answer to these questions in one place, right? Instead, they're independent pieces that give you sort of part of the answer, and you can put those pieces together to answer a question that maybe no one's ever thought of before. So this is a really interesting property of knowledge bases. They're modular and compositional. You can answer complex questions. So nowadays we're making enormous strides using large language models. So instead of a learning process based on sentences and semantic parses, we do a lot of things by basically just taking text and then building a large language model, and we can solve problems with text in and text out. And of course, one of the advantages of this approach is that it scales extremely well, and you can do much more powerful things when you have very large language models. But a disadvantage is that the knowledge in this sort of system is quite different. So in this picture, I've made it look like books, but really it's some monolithic set of parameters that all interact very closely in ways that we don't understand. So the knowledge is monolithic, not modular. It's expensive to change it, okay? And it's, of course, difficult to explain where an answer came from. So this is a disadvantage of this. And there are times, even with a domain like GeoQueries, where you're answering questions about geology, where you might need to update knowledge. So if you're asked questions about the border between Ukraine and Russia, you want to be able to change your knowledge base if Putin loses. Here's a proposal, and this isn't a new proposal. This is something that many people have been working on for many years, to combine the best of both worlds by having a system which does use something that looks like a large language model, but has some sort of explicit representation of information that has some of the properties we have for a knowledge base. So one idea is to basically encode some corpus as a set of independent memories. And then when you get a piece of text, question from the user, let's say, you explicitly retrieve something from that corpus. And you bring it back to your AI agent, which then does some processing and produces some text. Okay, so this is the same API as a very large language model, but the advantage is that these independent memories can be modular. They can be things you can update. So they could be little fragments of free text that are sort of independently meaningful. They could be something different. They could be tabular data. They could be structured facts or images. And there's the potential for some kind of compositional reasoning in this setting. So that's the motivation. And now I'm going to spend the rest of our time talking about this approach to NLP. And I'm going to do this in a very particular way. So I know there are a lot of people here that have worked on this problem. I'm going to talk about some things and not other things. Don't feel bad if I leave you out. Really, I'm just trying to get everybody to dinner. So let me start out by talking about why this problem is challenging and why it's challenging to do in a neural networks context. Okay, so here's my idea. So I'm going to code the corpus as memories. All right, I'm going to do a retrieval, and of course I'm going to do a retrieval in a neural setting, okay? So the way we do the retrieval is we take our documents, we encode them with a neural network into some sort of dense vector, okay? And then when I get my input, I'm going to also encode that, and I'm going to do some sort of like nearest neighbor in embedding space, okay? So that's the way I retrieve things. Once I've retrieved something, then I'm going to do some additional processing and get the output. So you want representation learning to, give you good encodings for these independent memories, okay? And you want to get there by doing gradient descent, but it's not very practical if you have a very large corpus, okay? So the problem is, this output depends on everything. It depends not on this, only on this input X, but all of these other documents. Even the ones that are distant are going to be connected in some way. So if you try to do gradient descent, the size of the computation graph grows with the size of the corpus. So that's okay for 100 or maybe 1,000, maybe 10,000 things, but you can't do it for a large corpus. So how can you fix this problem? And again, this is sort of like a short recap of different approaches. So one approach is, well, let's not worry about learning representation, or let's learn a representation some other way. But crucially, I'm basically not going to, go through and, push the error signal. Got it. 5 days, thank you. I'm not going to push the signal back through the entire corpus. All right, I'm going to fix that whole retriever process. So one really nice paper was by Urvashi Khandelwal and some other folks in 2019. So what was stored here as a memory was the state of a language model just before it output a token, together with the actual correct next token in the corpus that it was processing. So that's the memory, okay? And what you basically did is you basically took your current state of the language model and you retrieve a similar state, and then you fuse the prediction, the next token associated with that retrieved state with the prediction you want to make somehow. So this was a very simple idea, and it turned out to be very powerful. So it substantially reduced perplexity on a bunch of language modeling tasks. And one thing that was really cool about it, so remember, part of why we want to look at this kind of retrieval augmented approach is we want to be able to change the behavior of the system by changing the memory. So one thing they showed is that you could reduce perplexity. Well, you could learn on one corpus, and then you could switch to another corpus. Your perplexity goes up because you're out of sample, right? But you could also process that new corpus or something related to that new corpus and update your memory. And that would give you gains in perplexity on this new domain. So it was a great example of why having that kind of memory could be helpful. So around the same time, there was another very nice paper describing a system called dense passage retrieval. This was from Danqi Chen's group. Everything about that system was really different. So it was looking at open book question answering. Okay, instead of using the state of a neural network, they used the representation that was produced by a trained supervised retriever that was trained to match questions with passages that contain the answer. The things in the memory, or the way the memory was used was also different. You used the vector that represented a document as a key, and then you pulled out the discrete document and you basically sort of appended it with to the input, and then did sort of standard machine reading approaches. So everything about this was different except for this main idea that you're going to solve this problem of doing retrieval augmented learning by doing fixed retriever, okay? So this was another very successful system, got very nice results, was widely used. So this is one of the possible solutions to building a retrieval augmented model. I'm going to talk about a couple of other ones. Here's another one. So another idea is to basically make the system simpler by not having an encoder at all, okay? So instead of encoding let's say a definition of every entity in a knowledge base, what you're going to just do is store just a single vector for each entity, okay? And you're going to use a neural embedding just completely learned by the system as a free parameter in your system. Okay, so there was a couple of systems, and I'm going to dive into these a little bit more, but briefly, entities as experts was one such system. You had a vector that was learned that represented every entity in a knowledge base, or the million most frequent entities in a knowledge base. And you did retrieval, just this kind of standard way. With a million things, you could even do sort of attention with a big accelerator. And this was very successful for question answering problems where the answer was an entity. And then later there was some other work where that idea was extended. You added an additional memory where you had things which represented knowledge-based triples. Let's kind of dive into those things a little bit. So let's first talk about entities as experts. So what this model looked like is what language models always look like nowadays. It's a transformer, and the transformer had some special layers. And what those layers would do is, instead of attending over the contextual encodings at the previous level, it would attend to another large memory which just held these entity encodings. So you can think of these as just another set of contextual encodings to attend over, and those representations are learned over time, and they're shared, of course, by all the documents. So in this sort of system, there were actually two kinds of tokens, if you like. There's one token that corresponds to normal words. There was another token that corresponded to an entity ID. So entity prediction is like token prediction. So the pre-training task involves text along with some entity IDs. And the pre-training task was derived from Wikipedia text using hyperlinks as a signal for the entity IDs. And then you take the final thing and you fine-tune it on questions, like where does Charles Darwin live, and there will be an entity mask, so you're predicting an entity as the answer. So that's entities as experts, and the fact-injected language model is actually quite similar. So it basically takes entities as experts, and it adds another memory, which is accessed in a similar sort of way. So this memory is actually a key value memory where the key is a subject entity and a relation, and the value is an object entity. So the entity embeddings are all shared with entities as experts, so it's the same set of encodings. The relation embeddings are learned. This lets the system essentially access a knowledge base within the computation of a transformer. So this is the fact-injected language model, which was earlier called FACS's experts. And here's some numbers, okay? So I've highlighted a few of these. So one interesting comparison is comparing it to a standard large language model you trained to fine-tuned on the data set to just answer questions directly with its parameters. So we see that system does better than that, and it also improves over entities as experts. And these models are much, much smaller. So this is a model that's basically the size of a BERT model. And interestingly, the performance is coming from very particular places. So if you kind of drill into the subset of questions that can be answered in principle, okay, with the information and the knowledge base we were using, all right, which, again, for complexity reasons and, scalability reasons, this was a knowledge base just involving 100 frequent entities, 1 million frequent entities, and about, order of 1 million facts. If you look at the subset of the questions that could be answered, all right, the performance is dramatically better, okay? So this works, okay? And one thing that we showed in this paper was that you can actually edit the memory and make changes in behavior. So one experiment is basically to look at some counterfactual questions that have a counterfactual memory associated with them. So you could take a question like, where was Charles Darwin born? And change the answer. Okay, we're going to say Germany instead of the UK. This is not the right answer. The question is associated with something in the knowledge base, and we're going to change that too. Okay? I'm going to just do this for everything in the test set. I'm going to change the answer. I'm going to modify the corresponding fact in the memory. All right, I'm going to do it for everything where I can sort of find an answer. So once you change the memory in this way, performance drops from mid-50s to nothing. Okay? Okay? Then when you plug in the updated memory, performance goes back to almost where it was before. Okay? So modifying, updating the memory works. We also looked at adding things to the memory. So adding things to the memory is a little bit more complicated. What we did is we tried to hide as much as we could of test-related facts during training. So what you do is, if you had a question like, where is Charles Darwin born in the test set, then you would eliminate those triples from the knowledge base, and then you'd also go through the pre-training data. This was a system that was learned from scratch, so to go all through the pre-training data and everything which contained the two entities, an entity in the question and entry and the answer entity, would also be removed. So you'd filter out that data and then you retrain the whole system. So this is the performance of the original system, and then if you do this censoring of the data, performance drops a lot. It still gets some things correct, presumably from making reasonably plausible inferences. So a name like Charles Darwin, where could he be born? Some English-speaking country, not a bad guess. And again, if you insert the facts back into the knowledge base, you recover most of the performance. So going back to this history, this is another approach, okay? And it does have one important disadvantage. And the disadvantage is scalability. So you have to learn a novel representation for everything in your memory. In contrast, if you had some piece of text that you would use to derive that entity, then it's a much more statistically efficient. You just have to understand language, right? And then you can derive a representation from the description. So it's a possible solution, but like the solution where you basically use fixed retrieval, which sort of seems like a limitation, it's a not completely satisfactory solution. So here's another approach. All right, so this is approach 3. So approach 3 is a variant of approach 1. So instead of using a fixed encoder, supposing I do this. Supposing I pretend I have a fixed encoder, retrieve a bunch of things, but then I'm actually going to re-encode those things, and I'll back propagate my error signal through the encoder for those few things. So let's say I just, re-encode the nearest K documents. All right? So that's efficient enough to do. The problem is, now I've changed the encoder, okay? So the encoder is different. So the whole corpus now needs to be re-encoded, okay? And to do this sort of indexing on to do this retrieval on a large corpus, you need some sort of approximate nearest neighbor search. So you need to do indexing. So that's an expensive thing to do. So this is like feasible from a training point of view, but it's not correct. So how far can you get away with doing this? So another approach is to basically do this using a stale similarity function. So you don't worry about the fact that the encoder has changed. You just, let it stay stale, let it be wrong, keep retrieving things from the same index, and then every once in a while we're going to go ahead and re-encode the corpus. So there's sort of two parallel processes here, one which basically goes and re-encodes the corpus and gives you a new index, and another one which is training the system in this particular way. So there are a number of systems that have done that. So Realm from Kelvin Gu and Kenton Lee and some others at Google. And there are a number of systems. There was one that was just published a few weeks ago that uses this kind of iterative encoding. So this iterative re-encoding of a corpus is another possible approach. It's sort of like expectation maximization for people that remember that approach. It's got a couple of problems. So one problem is it's hard to do this unless you have pretty good retrieval. Because if you have bad retrieval, then you're re-encoding things that have nothing to do with the problem. So you need to start from a pretty good starting point. And the other problem is that it's just really complicated. So people have done this, but it's not really something you kind of want to do unless you're expert. So having these two processes, it's no longer, you're just downloading this Hugging Face model and fine-tuning it. It's just complicated. So because of that, not many people have used it. So here's another solution. So this is actually relatively new. The other solution is to say, well, okay, we may need some sort of stage training. How many stages do we need? I don't want to keep re-encoding things iteratively, in sort of like a independent process. What's the minimal number of things we could do? So let's try doing 2. So in 2 stages, what you do is the following. So the first stage, I'll call retrieval training. So what you do is this process that I described before, but for a small batch of documents, whatever can kind of fit in your accelerators. So we're going to retrieve from a small subcorpus, and we have to choose that subcorpus carefully. It does have to be useful for the task you're going to do. And we're going to propagate our signals back and thereby train the encoder. So once the encoder is trained, that's the first phase. We fix the encoder. So now we're basically back to approach 1. We now have a fixed encoder, and we're going to fine-tune the rest of the system. So this is another approach, and this is actually pretty recent. There was an iClear paper that I'll dive into in another slide or two from, I guess the work was done last fall and published this spring that used this approach. And there's another paper which came out, roughly concurrently from Danqi Chen's group, which used the same idea, but again, in a very different setting. So in our setting, the memories here were entity mentions in some context, okay? And in this other system, TRIME, it was more like the K-nearest neighbor language model. The things in the memory were the state of a neural network modified to make them more retrievable. So the encoding is basically modification of that state. And they evaluated on language modeling and machine translation tasks. So let me dive into the mentioned memory system a little bit. But the key point here is this is a much simpler training process. That's the advantage. Another advantage is that this scales up a lot better. So we can learn parameters for hundreds of millions of memories in this approach because they're derived from text. One disadvantage is you still need to kind of figure out what your batches are going to be for the retrieval training. In practice, that doesn't seem to be too hard, but we don't know. So here's a little picture of what goes on. Again, this is just a transformer with another special layer that attends over a memory. And the memory in this case are mentions of some entity in context. And here's some numbers. Okay, this one, bottom one is our system. So there are two variations, one which basically retrieves from the memory once, and one which retrieves twice. So the intent is that the one that retrieves twice might be able to do better at sort of multi-hop reasoning type problems. So what you can see here is, again, it's a big improvement over a closed book language model. It also improves over entities as experts. And one case where it seems to perform extremely well is on entities that don't appear very often. So for entities as experts, there's not a lot of information to use to train representations for those things. So rare entities are hard for that sort of system. So this is the basic idea, and another thing that turns out to be interesting about this is that you can train it on a smaller memory. We trained it on something like 40 million entity mentions. And then you can extend it to a much larger memory by just encoding more stuff. And that does improve performance, and you get a pretty consistent improvement as far as the system can handle. Okay, and also importantly, performance is very similar on entities you saw in training and ones you did not. How am I doing for time? Anyone know? I'll just keep talking. Perfect. Okay. All right, so this has been a little bit of a whirlwind tour. So we've covered all these systems. They won't all be on the test. But I do want to say a few things about this. So I've been talking about one dimension of these things. So my story has been, that the important thing is sort of how these systems are trained. And my story has kind of been that this two-stage training is sort of an interesting contribution. There are a lot of other properties of these. So I want to kind of just talk about them briefly. So there's one set of systems where what you encode is a state of a neural system, and what's associated with that is usually a token. So these seem to be good at reducing perplexity for language modeling tasks. They seem to be good for machine translation. They don't seem to be useful for many other tasks. Another set of tasks chooses as the memory documents, and those documents are just retrieved and they're used basically as a list of tokens. So you're retrieving the discrete form of the document. So these are retrieve and read sort of systems, and they seem to be very useful for open book QA. And then they're the systems that I kind of dove into here, largely, that are part of my work, where what you are encoding is something like a knowledge base, entity or a knowledge base triple. And these seem to be mostly good for QA for tasks that are very entity-centric. So the tasks that we were looking at here, trivia QA, the answers are almost always entities. Complex web questions, the answers are entities, entity questions. Again, so these are a very specific subset of question answering tasks. So here's the motivation that we had. The motivation was to be able to do question answering or NLP more generally using knowledge that had the characteristics of a knowledge base. So we want things that are modular, that you can independently verify and can be combined. So there are a lot of interesting questions that are about entities where the answers are entities, but there are a lot of questions that are not about entities. So these are just a sample of questions from the natural questions data set, which was derived from questions that people ask Google. And many of these things just don't seem to fit into that kind of mold. So I and my colleagues started thinking, so what could you use that would have the characteristics we want? So we want to be able to create them at scale, right? We want to be able to combine them compositionally, like knowledge-based facts, and we want to be able to use them in a more general setting where we can answer general open book questions, not specifically entity questions. So there's actually a handful of papers now that are moving in the same direction with respect to answering this question. So the new idea about what to put in these memories is basically questions and answers. So I'm going to dive a little bit into this idea in our last few minutes. So there are a couple of papers here. One is proposing this, this representation called a QEDB, question explanation database, and proposing using this as a memory. And then there's another paper, which is a more technical paper about how to use these things in a transformer. So there are a couple of papers involved here, and let me kind of step through the key ideas. So one key idea is that questions together with their answers are a lot like triples in a knowledge base. And they're even more like triples in a knowledge base if you add a little bit of annotation. So there's another project at Google called QED, and in QED, one of the goals is to annotate questions with information that let you explain why an answer was relevant. And one of the key things in that was to basically code entities and questions and align them with entities in a passage that contained the answer. So that's indicated by these colors here. We've got a question, we've got a passage, we've got an alignment of the things in the question with things in the passage, and we've got an answer. Okay, so this sort of explanation for a question answering looks a lot like a knowledge graph relation. Okay, there's some differences. So the set of relations is open. So there's a relationship that's suggested by the question, who's the actor that plays, you know, X and Y, all right? But there's not a fixed set of things that are going to be, fixed set of relationships stored in the knowledge base. The other thing that's interesting is relative to a knowledge base. So most knowledge bases have traditionally been built by looking at what data is available. So data that's sort of like in schemas that are designed by database people and then integrating that. So basically the knowledge base is populated with what's easy to put in databases. So here this is focusing on what people ask questions about, all right? So the information that is going to go into like a database of this sort, a QEDB, are things that people write about and ask questions about. The other thing we can do is we can add a little bit of processing. So it's a little hard to entity link entities that appear in questions because there's very little context. But we have pretty good tools now for recognizing exactly what entity is associated with a string like Peter Dinklage in free text. So we entity link the passages, which then now gives you also entity links for the questions. All right. And we built a database using this existing resource of generated questions from Facebook called PAQ, probably asked questions. So even though these are generated questions, they're generated based on data from actual questions that are posed by crowd workers or Google users in some cases. So this is a system so we can generate this sort of information at scale. So the other part of this is a learned question retriever, so you can sort of match two questions and see whether they're the same. And I also just want to kind of point out, I'm not going to talk too much about like the way you might want to compose these things, but it's pretty clear to see that you can, right? If we look at this sort of this sort of graph, you can see that this contains the information I need to answer a question like, what channel could I watch the character Tyrion Lannister? It's there in the graph, so, the details are in the paper. Okay, so my claim is that this is actually going to be much better aligned with real-world questions than a traditional knowledge base would be. So here's one experiment which gives a little bit of support for that. So the first set of numbers I showed you a few minutes back for this fact-injected language model, I looked at performance, which was in the mid-50s, I guess, pretty good, for a data set called Web Questions SP. So this is a data set of entity-related questions. So they have to have an answer that's an entity. They have to have a semantic parse. And, you know, this is actually a pretty stringent constraint if you look at the paper that introduced this. The Web Questions data set was pulled from looking at Google Autosuggest, and 99 questions out of 100 didn't sort of fit this criteria. So it's a pretty selective set, okay? And I said that, for the questions that were really represented in the knowledge base, the system did even better, okay? So this red line here for film got up into the high 70s. If you look at the things that are sort of just perfectly selected to be exactly ideally aligned to the knowledge base you have, okay? Now, if you go to a more general case, then film doesn't look so good. So this blue line is using a similar sort of system, but a question-answer memory. So performance is not quite so good in an ideal case, but it's much better in a case which is more plausible. And Trivia QA is also a very entity-oriented data set. And I guess this yellow line is basically using exactly the same model as for the question memory system, just using a different memory that's derived from knowledge bases. This is, I think, support that this is giving you more flexibility and being able to answer more questions more robustly. It doesn't really ask for what happens if you go outside the space of entity-oriented questions. We're going to do that next. So let's look at the natural questions data set, which are these things like, what is hops used for in brewing? So here are some numbers. So I know there are a lot of numbers here, but let's kind of step through them a little bit one at a time. So I mentioned that there were 3 papers that are using these sort of question-answer memories now. One is super recent, came out last week or something. I have nothing to say about it. I haven't even read it carefully yet. Another one was prior work to ours. It was a system called Repack. So this used an iterative encoding approach. So Wenhu Chen was involved with this project. So of course the experimental results are better. They're actually much better for certain types of problems. So if you have a problem where you don't have a lot of training data in the downstream task, then there's a big improvement for our system over earlier systems. But I think the other and maybe more important thing to do is just kind of focusing on these things. The performance of these is actually pretty good, right, on natural questions relative to other systems, okay? It performs much better than the closed book approaches, even with the very largest, newest language models, okay? So that's a substantial gain over systems that are hundreds of times bigger, okay? It's actually pretty competitive with open book approaches. I'm hiding one thing here. There's a technique called fusion and decoder. So the clever idea behind fusion and decoder is basically using a particular kind of sparse attention that's very well suited for question answering. And it lets you pull information from many, many documents. So in fusion and decoder, you're retrieving 100 documents. It's an expensive model, but it's very effective. So fusion encoder does do better. I think we can actually do better than these results reflect. Part of the problem is that we're using a relatively limited set of questions. So the probably asked questions from Facebook, they ran a question generator on all of Wikipedia, most of Wikipedia, and they generated something like 250 million questions. And then they threw away 3 out of 4 because they didn't satisfy certain kinds of consistency requirements. So this is still a relatively limited set of questions, and part of the problem, I think, with sort of getting this 5% difference, or maybe slightly larger now if we look at the numbers for Atlas, is just the recall of the questions in the database. Okay, and there are also results in the paper that show that this technique performs pretty well on multi-hop data sets as well. Okay, so this is a quick survey. If I ever post these slides online, which I think I'll try and do, the links will be here. I think you can probably get most of these by just kind of going to Wikipedia or Scholar. So just saying a few words about where this may be going in the future. So there are a couple of really interesting directions. So I've talked about memories that are based on knowledge bases and text and question-answer pairs. There's no reason why we have to be limited to those kinds of objects. This approach also works for other types of things. There's recent work by Wenhu and others using a multimodal memory for question-answering tasks that are information-seeking tasks, where the information you need is partially encoded in an image. So now you've got a memory where essentially everything in the memory is a text-annotated image, and they're both encoded, with the same sorts of system, a visual transformer for one. Speaking of vision, a visual transformer for one and a text encoder for the other. And you're doing a similar sort of retrieval and then text generation task. Another really interesting application of these things, or another interesting reason for using these, is that if you look at the retrievals, you can, in principle, find something about where the source of the answer is. So this is not always trivial or easy. So if you look at something like Fusion Decoder that pulls out 100 documents and runs them through a very large language model, it can hallucinate an answer that's not in the data. It can ignore things that are in the data. It might be using things in the data in some weird statistical way that you don't understand. But there's a hook to understand how the systems are working. And there's been a couple of recent papers that look at ways of evaluating whether a system retrieves the correct provenance for the information that it's generating. And supports that the claim it makes. So one thing that as far as I know, people have not done yet is integrate this kind of retrieval augmentation with in-context few-shot learning, like the kind that GPT-3 and other big models do. There's a little bit of work on this very recently. So the Atlas system, which came out a few weeks ago, does few-shot learning with small amounts of fine-tuning, not in-context learning. There's another paper which does in-context learning with a fixed retriever that's very recent. But I think this is another kind of interesting direction. So I'm going to stop now. Thank you very much for your attention.
So we have time for maybe 1 or 2 questions.
Thank you so much for your talk. I just have a quick question on the retrieval process. I wanted to know, what's current methods for reducing the calculation complexity in the retrieval process? Because I believe that to search in the corpus of knowledge, you have to do some similarity calculation and stuff.
Yeah. So my personal take on this is that the retrieval process is probably best done by merging different sorts of information. So probably it's some combination of, for question answering, supervised learning, and then use of the whatever downstream task that you have. So I think you do want to be able to sort of fine tune the retriever using information from the downstream task. But I'm also aware that there may be many different settings that this is important, where the retrieval might have to be done differently. So all the experiments I've talked about, in this talk are on English data. So in English data, we know more about how to do retrieval. We've got large annotated data sets. And if you move to some, low resource language, or even if you went to kind of specialized domain like science, then what you want to do for retrieval might be quite different. So, I think there's a lot of questions about how the retrieval interacts with a question answering system. Dirodua is nodding in the back of the room there. I know she's working on this problem.
Okay, do we have one more question?
Thanks, nice talk. This is a small question about the last thing that you said, that you weren't really aware of things that looked at in-context learning with retrieval augmentation. And I wonder how you view exemplar selection in prompts, like given a test query, some test instance, I select using some retrieval method, some training instance to put in a prompt. And is that not what you're talking about, or are you doing something else here?
Oh, yeah, no, I was thinking more about the problem of retrieving background information as opposed to retrieving information to put in a prompt. But I kind of see your point. So there is some interesting work on prompt retrieval. So Jonathan Barent's done some stuff where you looked at basically sort of like the reduction in perplexity that you get, trying to approximate that. And there's actually a paper coming out in this fall's NeurIPS that's looking at a similar sort of approach for kind of general language modeling approaches. So I think this stuff is relevant. Yeah, like I said, I'm trying to get to dinner. I can't talk about everything. So, but I agree there are interesting connections between those two problems.
Okay, so for the sake of time, let's thank William Cohen again for the wonderful talk. All right, so the last part, please do not leave. Right now is the most exciting thing that will happen is that we're going to announce the 3 best student paper award, best paper award out of the 88, right, accepted papers. So it's a very selective award, and Michael is going to tell us and close.
Okay. Feels like the Oscars, holding this folder. Okay. So yeah, thanks again for coming, everyone. We want to thank our sponsors, Amazon, Megagon Labs, Appfolio, and us. And now we'll present the 3 named awards for the sponsors. So just to review, thank you to all the a review of the reviewing. Thank you to all reviewers. Each person read a few of the papers / abstracts, ranked them, and then out of the top 10 that were ranked, a secret committee looked through and picked 3 to get these named awards. So we'll be presenting we didn't want a hierarchy of sponsors, so there's 3 best papers. So we have the Amazon best paper, the Appfolio best paper, and the Megagon Labs. So I'll make it fast. The winners are, for the Amazon best paper award, the winner is, it's okay, whatever. Contrastive novelty learning. Albert Xu, Xiang Ren, and Robin Jia. So yeah, come up. We have an award for you. Yeah, come all up and get a picture. Congrats. Okay, yeah. And next, the Appfolio Best Paper Award goes to Conda QA by Abhilasha Ravichandar, Matt Gardner, and Anna Marasovic. So yeah, all present authors, please come to the stage. Congratulations. Congrats. Congratulations. And finally, the Megagon Labs Best Paper goes to Empowering Language Models with Knowledge Graph Reasoning for Open Domain Question Answering by Zunyu Hu, Yichong Xu, Wenhao Yu, why aren't you clapping? Shuohang Wang, Zi Yang, Chengguang Zhu, Kaiwei Chang, and Yizuo Sun. Yeah, authors. Are the authors here? Are any of the, did they leave? Okay, Kaiwei, you're accepting it. What? Oh. I was like, why do you want me in the picture? No, I didn't write it. Okay, Thank you all reviewers, other speakers. Thank you all for coming. And yeah, that's it.